about that. But if we were to do it the way we did it, that we set out doing it with our text, right? This was a hypothesis, and we still get the exact same test statistic, okay? So when that doesn't change between these two cases, and again, the reason we multiplied the p-value by 2 is because when you do this test, over here and some area over here, right? You're gonna have twice as much when you do the test like that. And I don't know if you ever encountered this, Matt. If you use those templates that were given in chapter 9, right? We can build the templates.
Normally it's if you have a one-tailed test, you get a p-value, and then you take the min of the upper and lower tail test and multiply that by 2. Because when you do a two-tailed test, you have to be, it's a more precise measure because of the area being split between two sides. So 95% one-tail test, you have that 5% window to fall in order to fail it, in order to reject the null. So the 95% two-tail is only 2.5%.
Yeah, this is what they're really struggling with. Some people really struggle with. Why is that twice, the value of the minimum here, right? And I just sort of got it after a while. And another reason I would argue, and I sort of agree, obviously, what Matt was saying, but we're actually dealing with the exact same Z statistic in the test, right? And it depends on, are we looking at this set of hypotheses or this set of hypotheses? But the actual value of the test statistic does not change at all.
And so the reason why you take the minimum, that's kind of, if it's a minimum, what people are struggling with, you're calculating already your upper and lower tail test. So you could be calculating your lower tail on an upper tail test, and if you're calculating your lower tail on an upper tail test, you're going to fail to reject that null all the time. That's going to be an incredibly high percentage value because your lower tail test, if you're looking at your upper tail test on a true lower tail test, your lower tail test is going to be closer to about 5%, and your upper tail test is going to be 95% or something like that. That's why you're taking the minimum of the two, because you don't know when you do a two-tail test whether you're going to fall within the upper tail or the lower tail of the two tails.
Is that helping at all? I thought we would just cruise over it one more time. Listen.
I guess the way I'm trying to picture it, and I could be off base, but at least it's helping me understand it, is that because you're telling me that you use the same test statistic for both equations, and on the two-tail, you split the alpha across the 2 in order to counteract the split, the 1/2 on each side, you double the min value. So when you take the 2 and the 1/2 out of the equation, you still get the same end result. Maybe that helps to explain why you double the 1 because you're splitting the alpha.
I think another way to look at it, if you don't double, you just compare your p-value instead of 0.05 to half of that, 0.025, which is that portion on the right side.
If we're talking about 95%, and we're going in an upper tail test, a 95% upper tail test, your critical value is going to be 1.64. Because there's going to be 5% on the left of that. So if we were to pull the value somewhere around here and we get that p-value, now, if we're doing a two-tail test, our critical value is now 1.96. Because we're sharing this area on both sides. So instead of having 5% to the right, now we have 5% to the right and 5% to the left. So our p-value is going to increase because it is a harder test to pass than a single-tailed test. So now we had an area of 5% where we could land in, and we go from an area of 5% we can land into an area of 2% we can land in. It's a more precise test. Because this 2.5% we get on the back end, it doesn't matter because we're never going to fall within that realm on this distribution. So the test becomes more precise. So if our test becomes more precise, then the probability that we pass our test, the probability that we fail to pass our test increases.
That's why you double it.
That's why you're doubling. Because it's not a probability that we pass a test, it's the probability that, it's not the probability that we fail to reject the null, it's the probability that we reject the null. I mean, we don't say that. It's not think about it as, you want that number to be lower, we're trying to minimize that number. So yeah, so it's the probability that if we were to reject the null, we would be wrong. So the more precise that test is, that number has to increase because it's a harder test to pass. It's kind of the best way to think about it.
Yeah, the first time you see that on the Excel spreadsheet, that can get a little confusing. I certainly admit that it got me the first time I saw it. But
There's just no formula, there's just no value, there's no formula within in Excel already pre-built to calculate the p-values. So that's why you have to take the min of the two. It's hard to think, we think of passing a test as getting higher on the percentage. When this, we're trying to minimize that percentage scale and get lower and lower and lower. So the lower we get, the more precise the test is. The test is less area now, so we have to double that p-value.
So I hope that helps. But the one thing I want to do, I just wanted to recap, and we're going to be using those same worksheets again, the same templates. So let me get you to open up quality. This is in chapter 9. And this is what you will find. You will find 4 columns of data, sample 1, 2, 3, and 4. Okay, I just added this to my worksheet here. Okay, I just made this up. All right, so here's the problem. Arlo manufactures shampoo for dogs and cats. They recently conducted 4 samples, and we have the sample results over there. The company wants to be 95% certain that processing line 3, so only deal with this column here, sample 3, okay, is producing 12-ounce bottles. And the standard deviation of the production process is known to be 0.21. So what is this last sentence telling us?
Giving us a known population.
Right. It's telling you that we know the population standard deviation. Okay, so that ought to set you up. Look over there. What kind of tests are we going to do? Okay. Now, what I would tell you to do is pull up your template. Okay, you've got 3 templates that we worked on. And which template you want? You want the template where the probability, I'm sorry, where the standard deviation of the population is in fact known. You have those? You remember what they were? Yeah, this is a golf test. So I'll let you do it. I just literally pasted that template, that part of the template, right into a second worksheet. Okay? And I took that 3rd sample, pasted it over here. And with a little bit of finagling, the thing worked just fine. Okay? So let's talk about our research hypotheses. But you can actually do the test without even worrying about what the hypotheses are, right? You have the template, right? The question is, you really need to figure out your research hypotheses to know how to read the values from that template. But you can clearly just run the test without even knowing what your research hypotheses are. So that's what I'm asking. What are the research hypotheses based on this? Well, what is it? Are we looking at a 1-tailed test, upper, lower, or are we looking at a 2-tailed test? We're looking at a 2-tailed test, right? We didn't specify whether or not we're arguing that that one is greater than the other. We just want to know, are they the same, right? The production process could be out of control in either direction. It could be putting too much shampoo in the bottles or too little shampoo. And we weren't specifying one direction or the other here, right? So we're going to assume this is a 2-tailed test. Okay?
So we want to know if they're equal.
Right. We're setting up our hypotheses like this over here, right? The null hypothesis is going to be that the sample mean is in fact equal to the hypothesized mean of what I said was 12, and the alternative is they're not equal. And we'll and if the process is producing either too few ounces in the bottle or too many ounces in the bottle, then our test will pick up either end of that. Okay, so we're not arguing like we did in the other problems where there's at least 12 ounces, right? We're just saying, are there 12 ounces, right? Is the sample, the set of samples here, right? Is the mean of that equal to the hypothesized mean over here of 12 ounces or not? Okay, so let me go back to the template. Okay, that's literally all I did. I drug, I copied part of that template over here to this worksheet, and then I pasted that sample. I pasted that sample through. Every time I say paste it up now, that's it. So I pasted this, this column in right over here, and then the statistics just they were before, right? We didn't have to rewrite any of these statistics, right? We still have the count, the sample mean, right? What I did have to do was this, right? I color coded this. This is a reminder to myself. I have to enter the population standard deviation. This is not a formula. This is something we have to enter, and you have to enter the hypothesized value here if we're going to use this template here. The rest of these formulas were already built in our template for us. Okay? Yeah.
Just in the statement itself, I thought the null was the opposite, so it would be it's not equal to 12.
Yes, it's not equal. The alternative is that they're not equal. So, you guys have trouble pasting it? You're getting the data? Everybody got this? Okay. So what test are we using? We're using this test, right? We're using a two-tailed test. Okay. We're going to get all these values anyway, right? So the p-value of the two-tailed test is right here. So what do? Do we accept the null? Do we reject the null? We reject it. Or as economists might say, what? We fail to accept. So we're gonna reject the null hypothesis that these bottles, in fact, they are not meeting that. That the sample, that one sample, right, sample 3, in fact, did not have 12 ounces in there. Okay, everybody get that? So I guess one of the points I wanted to make was, since we built all these templates, all you really have to do now, if you want to use them, is put them in a separate worksheet, paste your data, and it all ought to come out for you. And you can run the test before you even develop your hypotheses. Not that you want to do that, but right, we're going to get these results regardless of which hypothesis we decided to form here. Okay. Move on to the next one. No. Yes.
Which one to use races?
Illustrated.
Like the
Yeah.
I get it. I can plug them in.
It goes for the eraser.
I don't know how to read that and say, yeah, that's just kicking my ass.
Yeah, I have to read the book. I said to Amber, I'm done with time on Sunday.
This.
I could put-
So again, we decided that we're going to do a two-tailed test here, and we wanted to be, I believe this was 95% confident. Was that correct? Okay. So this is going to be 0.025 in this tail, and 0.025 in the lower tail over here, and then we're looking for. What's our critical test statistic? What's it going to be? What does it take to actually test this hypothesis? And what are those values at 95% when you have a two-tailed test?
1.96.
And this would be the minus 1.96. Okay. And what did we get for a test statistic minus 2.89. So our test statistic is way out here, right?
Okay.
Minus 2 point, can't read it over there, 2 point, what is it? 8.9.
Okay.
Okay, so we're in this region over here where, right, this is beyond chance, right? We didn't get this result just by chance. We got it because, in fact, the process is somehow out of sync. They're not putting enough shampoo into the bottles. Yeah, the sample of those 30 indicated that the mean was what? It was 11.89. So again, on our curve, this is what we said. This was you know, the hypothesized mean was 12, and what did we actually get? We got something way out here. The sample mean was 11.89. It doesn't sound like it's far off, right? But it's far enough off given the standard deviation to and the sample of 30 to conclude that this process is not producing 12-ounce bottles.
So if you want to put the answer that's in the tails, that's where you want to be. You are rejecting
The null.
the no.
Right? Anything in here, right? There's a 95% chance that that in fact you did get a result of 12, which is within these critical values here. And we would accept the null. If it's in either of these tails, we're going to reject the null hypothesis. Here, that was way down here, minus 2.89 was the test statistic. That was our test Z, and we were looking for something between this plus or minus 1.96. That's not what we got.
And so it's the 0.0038 being less than the 0.05, so you get that is.
Right. This is probability is 0.0038. Just saying, and that is less than our significance level of 0.05. So we reject it. Okay. Let's do another recap. This is still from how about this? Open up your administrator file. Again, you're going to have that column of salary in there. I just posted these notes on here so you can see what we're talking about. So in this sample here, we're saying that the national mean salary for high school administrator is $90,000. So 90,000, right? And what are we going to call that? That's not the sample mean, right? That's sort of the hypothesized mean that we're talking about, and that was 90,000. A sample of 25 salaries, so I can stop here. I now know that n equals 25. They're all from Ohio. The salaries in the sample differ significantly from the national average. What kind of a test are we going to do? Yeah, because we do not know what the population standard deviation. So we're going to do a t-test, and we have a template for that, right? When the standard deviation is unknown, hopefully yours is going to look like this when you bring it over. Yeah, help me out. Where do we get this template from? The order, yeah, from me, right? But it was from the orders data set, right? Again, all I did, I just copied that. I copied it, and I pasted it in the exact same place, so I didn't have to mess with the formulas at all. Again, you get the test result without even formulating your hypothesis, right? We still need to do that to understand how to read this. To do that, to list our hypotheses, understand what's going on here, but actually doing the test, I mean, this stuff is becoming easier and easier. That's what you're gonna find out in the coming days, that running these tests is really gonna become much easier as we move along. Like the ANOVAs, the chi-squares, setting them up and running them, it's gonna be very simple. It's gonna be the interpretation of the test is what's really, it's what we're really trying to test you guys on. You really understand what you're seeing when you see these tests. So here's our sample size of 25. Everybody get the same sample mean here? 85,000. And again, 85,000. Now we know what the sample mean is. 85.
272.
85. 272. Okay. So again, what's the question we're asking here? We were asking, are they different? So our null hypothesis, we're not looking at a particular tail. We're just saying, is our sample mean going to equal our hypothesized mean here? That's our test. And then A sub A is that it does not equal our hypothesized mean.
What was our alpha on the question? Did it give it?
There wasn't one.
I didn't get it. Again, you can run the test without even knowing the alpha, right?
You can't determine whether you're going to pass or fail, right?
Right. So I was gonna, again, when in doubt, it's 0.05. That's a good question though.
0.5, and that's specified that you would actually not reject the hypothesis.
We would
Not reject.
reject.
Well, would it be 0.25 each side?
No. This is why we've already made the adjustment.
So you're
for
multiplying it
210.
by 2, so you don't have to do so you don't have to multiply it by 2 in your head. So like you just said, there's 0.25 or 0.025 on each side. That's why we're multiplying it by 2.
So the word, the template's already taken care of that for you. Trust the template. Okay? So the p-value is giving you, if we're doing a two-tailed test, and we are, then here's the p-value. If for some reason we weren't doing a two-tailed test, if we're doing a one-tailed test, then we have different p-values.
Now I know why you doubled it. Now all of a sudden.
Okay?
Thank
Yeah, it's just gonna click. I mean,
you.
I said it a couple times, yesterday, and I know we weren't getting it. That's why I really wanted to just start again, but if you trust it, play with it a little bit, look at it.
Can you go back to the question, just give one example of what would indicate fail instead of failure? So instead of
Let's say this this hospital administrator was making a claim, hey, we got to pay our high school administrators more, right? They're not making as much as the national average. So that if we said something like that, if that's what he was testing, claiming that they weren't making as much as the national average, right? Well, again, if you want to set up your research hypotheses, I always like to think about it as, well, how am I going to make that test? He's actually claiming that, that Ohio, right, that the salaries in Ohio are actually less than the salaries in the U.S. Okay. So if we would set that up as a hypothesis, just think, where are we going to reject our test? Which tail is really going to be important to us here if we reject that test?
Left.
So this doesn't say like the significance level, so we just assume it's 5%
Yeah,
unless otherwise.
just assume it's 0.5. I apologize. I should have put it in
Okay.
there. But when in doubt,
Just use that.
well, I doubt I'm going to give you any problems where you have to assume that. Okay, but I just simply forgot to say it. But yeah, it's 0.05. Okay, yeah.
So then basically, we're rejecting that the salaries do not differ? We're saying that they're equal?
No, we are rejecting that they are equal. They are not equal. Why? Because we got a result here that's beyond chance, right? Think of it that way, right? It's how likely was this? This was not very likely, right? To actually get these kinds of differences wasn't due to some random chance. This was due to something going on probably in the state of Ohio. They're just not paying people enough for whatever reason. Maybe they have poorly skilled administrators. Maybe they don't deserve it, but the question is, you know, is the salary that where they were paying in Ohio equal to the salary that is made in the United States average?
So the answer is, you reject the no.
Right, so the answer is no, they are not equal. But again, if you would have set it up differently, right, if the administrator was claiming, you know, hey, the salaries in Ohio are less than what's in the US, then we'd be dealing with the one-tail test, right?
So in this, I'm sorry, in this case, if the sample mean was really 95,272 and the t-stat was a positive 2.14, it's still the same. We still come up with the same result. It's not equal, right? It's not
Right.
not because it's less than. It's because it's more than 2 standard deviations.
Exactly, it's more than 2 standard deviations away. The direction in this test, in this test for equality here, the direction isn't important. We're going to capture it if it's in either of these tails, right? If your observation, the sample mean is in either of these 2 tails, we're going to catch it. Where a one-tail test, we're just setting it up for one tail. And I agree with Matt was saying. Let me just emphasize that. It's a more stringent test when you set it up this way. Okay, it's more difficult to reject the null hypothesis when you really, put the areas of probabilities, in 2 separate tails. It's harder to actually get an observation in one of these tails as it would be if you just, declared it to be a one-tail test and then went about, assessing it. Okay, everybody with me on that? This was again, so this was our template about the standard deviation was unknown. So we went to that template. And again, if you look at it, right, if we look at these various, test statistics again, there you go. We did t-test, right? We used the t-dot distribution to compute these values here, these p-values. We actually used the t-test, not the z-test here. The same thing down here again, which is just 1 minus, so that was not a big deal. But that's what we used in the template to assess this hypothesis. We used the t-test, not the z-test. One more?
Oh, please.
So here's Bayview. So pull up the Bayview data. This is all coming from chapter 9 again. Again, I'm using some of this data for different purposes, okay? I think if you found in the back of your textbook talking about Bayview, they might have asked some different questions here. I'm just using the data that, to actually demonstrate something. These were not the questions asked in the textbook. I'm just using their data to ask some questions. So Bayview University conducted a survey, and they asked several questions. Did you ever copy homework from the internet? Did you ever copy on an exam? Ever collaborate on individual projects? And then the answer was also by gender. We're not going to analyze that today by gender. But my question is, the Dean of Bayview wants to know if the proportion of business students who reported they had copied, were copied on exams is lower than the overall university average of 27%. So we're looking at this column right here, okay, copied on exam column. We're formulating this hypothesis. He wants to know, is this lower than the university average of 27%? So what kind of a test is it? Yeah, we're going to deal with proportions though, right? We don't have any numbers to add up. We have no sample means or anything like that. So we're literally going to count these responses and we're going to get a proportion of how many cheated. So yeah, we've got a template for that, right? We've got a template that you can use to answer this question, right? Whether or not these differences are significant. And again, are we talking about a one-tailed test, a two-tailed test? One tail. And why is it one tail? Yeah, I mean, he's really asking this question, right? Is this, you know, is the proportion of these responses, is it lower than the university average of 27%? Okay? Again, I copied my template over here, and then I moved that column, or I copied the column over here. And what did I change? Well, again, I highlighted this just so there's no question, a reminder. I had to change this cell, the response variable of interest. I forget, was this male, female in our template? I changed that to yes. And again, capital Y doesn't matter as long as you have the characters. We had to change the hypothesized variable that was in the template from whatever we used it before. So I keyed in 0.27. And then we now have the statistics. But the question is, right, you've still got to read this, right? We still have to think about what are our research hypotheses here, okay? And clearly we're doing, right, the lower tail test. Right? In our example here, the university average is 27%. Well, he wants to know, is the sample from the business school less than that? And what was our sample proportion?
20%.
0.20. Okay. So again, for us to be able to reject this null hypothesis, we have to be way down here in the tail. And again, if I didn't say I wanted 5%. And so do we accept or do we reject the null hypothesis? We're going to accept it. All right. Family business students do cheat less, but not statistically significant. That difference is not statistically significant, right? You know, the mean we got was 0.20. University average was 0.27. Yeah, it's less, but you can't claim it's statistically significant. It's just less, okay? It's the same. Okay?
What is the because I recall presentations that the formulas are not being properly used. It says
Did you do that?
so I'm like,
Did you get 16 for your count of response?
The formulas aren't, did you put it exactly where you got it? I mean, it's the same cell and everything.
Did you get 90 for your sample size?
Is anybody having that trouble when they're copying and pasting from?
Yes.
Did you
Copy from exam, not copy from internet.
well, I paste as regular.
I think you want
That's what I was looking at.
Thank you very much.
Toshiba, I don't know why that would matter at all. You should just be able to. Does anybody else have that problem? Let's make sure we're all able to copy and paste these templates.
I'm wondering, what was the example from yesterday?
What problem did this come from?
Women's golf.
Women's golf. Women's golf?
Yeah.
I left women's golf alone and copied these and put in a template file.
Yeah.
Templates, I don't remember. Okay, was it the golf one?
Yeah, exactly.
Yeah,
Yeah, and rename, yeah.
That's exactly. Hypothesis test about a population proportion. That's literally what I named it.
Yeah, right, exactly.
Yeah. You're good now, right?
Oh, yeah, I just got the wrong form, thank you.
Not any problem. Not that.
I think the underlying assumption for this course, or the way he's teaching this course, is that we have not only, we've been exposed to statistics before.
Oh, interesting.
I mean, I haven't teach statistics even in high school. Like,
Yeah,
ever.
ever, yeah.
Research hypothesis. the Ace of A. Remember, I like to tell you that it's sort of pointing to the tail. If you remember
Yeah,
the
Greg was talking about it.
research
Like, yeah.
hypothesis.
So the first weekend, last week, it's like high school. This
Right?
This weekend,
Ace of A,
this is like undergraduate.
Great.
Next weekend is OMG stats. It says pile on as much possible points as you can now.
Oh my gosh.
Yeah.
Well, thank goodness.
So last weekend was easy. This one I'm kind of barely just hanging on. It's the light bulb's starting to come on.
Mhm.
It's okay, but.
Yeah, mine won't even begin to come out till tomorrow. I think you get bits and pieces of it, but it's like analyze, answering the question.
So this is our research hypothesis, right? This is what we're trying to prove. And so the way I think of it is.
But I can see myself literally writing this out
It's gonna give you the answer.
like he's doing exactly right there so I can answer the question.
Oh, it's so much easier.
If I skip that step, I get confused because I look at these numbers.
I just have to draw the picture.
So in other words,
I literally is what I think I'm gonna need to do, yeah. Doesn't take much time to do it, but it'll add a lot of clarity.
That would have been,
If they can come in with pieces
satisfactory.
of paper that already has that.
Okay? Because the sample mean would have been greater than the hypothesis. What's the problem there?
She's opening a separate instance of Excel. So in older versions of Excel, if you open an instance, you can't copy formulas from one instance to the other.
Yeah, I did.
I know.
So then now you just gotta click inside.
Doesn't make sense. Yeah, exactly. It will tomorrow. I'm 100% positive. Yes, that's what I do. For acronym.
Is everybody got this? Any questions? This is sort of the recap from yesterday.
Can you just do one more quick synopsis on why we're rejecting?
Why we were rejecting?
I'm not rejecting this one.
We're not. We're failing to reject.
Can you just say reject?
I know.
We're
seriously.
accepting the null, right? Because at 0.05 level of significance, right? This is what I tell you. You think of these as probabilities, right? Could this happen by chance? Well, we're saying it has to be less than a 5% chance. If it's less than 5%, then we're going to say yeah. Then we're going to reject. But because this is a 0.067% chance, no, that's not sufficient evidence to reject. If this was less likely, if this was really less likely, like anything less than 0.05, then we would in fact reject the null hypothesis. See, as far as how you can set things up in this case, well, again, think of the research hypothesis, right? What the dean wants to know is this alternative? This is his research hypothesis, that the sample mean for business students is in fact less than the hypothesized mean. And so therefore the null is just the inverse of that, right? The opposite of that. So the null is the sample mean is in
We're
fact
not referencing our
greater than or equal to
sample mean.
the hypothesized mean. Right, so just again, think of it. Here's the 27%. Right, this is the proportion here for all students. And anything out here, way out this tail, that's fine, right? That would still support the null hypothesis. If we got some result out here, and let's say business students were 33%, they cheated 33% of them replied that they cheated. Well, then we would simply accept the null hypothesis that business is in fact greater than. But we set this up as the alternative hypothesis. This is the research hypothesis that our observation was going to be less than the hypothesized mean. And again, the way I remember this and the way I like to think of it is the alternative hypothesis here, the inequality is really pointing to the tail that's going to give you the test of interest here, right? Right, I'm interested in this tail. That's going to determine whether or not we accept or reject. It's going to be that particular tail, not that it matters, but the lower tail, that's what we're reading here, right? We're reading this off the lower tail test, which is the lower tail. Hey, because it's 0.06, not 0.05, if it would have been less than 0.05, we would reject the null hypothesis. Right? We would reject this. So it's close, but not quite.
We're accepting the null.
We're accepting the null, yeah.
So you're doing 1 minus 3.
So we can't quite argue that, you know, the business students are cheating less than, you know, on the exam than any other university student. Even though, I mean, clearly the mean is less, but it's not significantly less. It's not sufficient. Now, if you wanted to prove it, I mean, you could have taken a larger sample, right? I mean, it's clearly moving in that direction. I mean, there's one thing he could have done, he probably should have done before you run the test. It's really not fair to go back and increase your sample size. But how many people would do that? I bet a lot of scientists would probably do that. They'd probably go, oh, I'm getting a result here. I just need more data to prove it, right? So you increase your sample size, and if you got the same, roughly the same sample mean that you did before, now you have a larger N, you know, this could easily become statistically significant at those differences. But it's not. Okay, for a sample of 18, it's not statistically significant. Is there anything else on that? All right, let me get out of here, and we'll start new material in chapter 10. So what we're really going to do here, by comparisons involving means, experimental design, and ANOVA, we're really going to focus here on some t-tests of two or more two sample means. We're going to show you how to run an ANOVA test. And by the end of the day, this is the last one we'll do this afternoon, we're going to do a chi-square test. Okay, so this is sort of where we're going here with this chapter. So we're talking about inferences about two population means when the standard deviations are known. Two population means when the standard deviations are unknown. We got to go back to my little chart over there. In the first case, we might look at some z-tests. In the second one, we're going to look at some t-tests. Max samples, okay, we'll explain that, but this is, you have max samples when the data is actually coming from, let's say, the same person, the same group, the same observation, okay? And again, it's very simple to do in Excel. It's just depending upon which test you decide to take. And then ANOVA, that's what it stands for. It stands for Analysis of Variance. Okay, and we're going to show you how to run some ANOVAs. And, you know, I like to think of where we're going. We've probably gotten over the hard part now. Okay, I'm trying to understand this at a conceptual level, you know, standard deviation statistics, test statistics and whatnot. These tests are going to be so easy to run that the real difficult part is going to be your interpretation of them. Okay, but running them is just going to be click, click, paste it up, boom, you have results. But the danger is you really understand what you just done when you interpret the results here. So I think the exception of chi-square, that might give you a little bit of challenge as far as setting up these. But most of these are just very, very easy to run here. Okay, so here's the first one. We're trying to make some inferences about two population means when the standard deviations of both are in fact known. And I'm going to skate through some of this very quickly because I'm really not interested in formulas. I'm not trying to teach you guys the formulas. You're going to come across these. We're going to try and get to the test themselves rather quickly, but we will pause on these formulas just so you can really get a sense for what they are. Again, just terminology, right? What are we doing? Now we're going to talk about, right? We're talking about population means, use of one, use of two, sample means of x bars of one, x bars of two, slightly different terms, but they mean pretty much the same things. And the expected value, all we're really saying in that bullet point is, right, that we're using our sample means as point predictors of the population means. And the expected difference between our sample means is what we think is going to be the expected difference between the population means. Okay? Standard deviation or the standard error here. Again, I'm going to drag you through this, but I think the appreciation you should gain is, look what we're really doing here. We're taking these two separate standard deviations with two separate sample sizes, perhaps. We're not requiring that our samples have the same ends. So what we're getting here hate to call it a pooled standard deviation or pooled standard error, but that's what it is, right? We're sort of averaging these standard deviations together, right? We get a little bit of weight based on how many observations they have. Okay, but again, you're not going to have to calculate this. You're never going to have to calculate this. You're not going to have to build these formulas or anything. Again, our point estimate here, we're saying the difference between those two, that's going to be that point, what that difference is. And this is basically telling us sort of the margin of error. Here's our C and alpha divided by 2 for the probabilities, and we've got this notion of standard error here, right? This sort of pooled standard error, and we still have our alpha level there, our confidence level, if you will. Again, we're not going to actually work with those formulas. So I'll get you to open up this home style data. And this is what you're going to get. We need to compute the sample mean, sample size. Go ahead and open up the home style. So hopefully yours looks something like this. Just have 2 columns of data, right? If we here's a template to do this. I'm going to make this available to you, but that's really not the test I would like to show you. All right, we can do another. We can do this another way, if you will. But again, we've got this template. If we want to do it, I think our textbook spends a lot of time actually building this for us. But as far as running this test, let's not use the template. Let's just run it. Data analysis, C-test for 2 sample means. Okay? You click that. And now here you go. Variable 1 is in column A, variable 2 is in column B, and we need to tell it what our hypothesized difference is. We're going to say it's 0. And then here, we don't need the standard deviation. Here we need the variance. Okay? We need to tell Excel what the variance is. Let's go back to the problem. We have a population standard deviations of 9 and 10. So what are our variances? If your population standard deviation is 9, what's your variance? Squared. It's just that number squared, right? The standard deviation is the square root of variance. Variance is the standard deviation squared. So our variance for sample 1 is going to be 81. And our variance for sample 2 is going to be 100. Here's our alpha of 5%. So let's go back to works. Now we know, I said that was 81 is the variance. And the variance for this was 100. Yes, there are labels in my columns, right? Because I copied the entire column here, which has the inner city and suburban. And I need to tell it where to put the output. I'll say put it right here. And click OK. And boom, there you go. So again, my point is, this is how easy it is to run these tests, right? This really didn't take much to do at all, right? I just had to literally paint them up. I painted up these ranges. Okay, notice they do not have the same number of observations. Inner city, we only had 36. Suburban, we had 49. You're going to get this in the real world, right? You may not always have the same data. So here's this ends in 37, so you know there's 36 elements there. This goes down to 50, so you know there are 49 elements in this. Again, Excel took care of all this. We didn't have to tell it anything. All we did was paint up these ranges, and it gave us the means, 40 and 35. The known variance is what we keyed in the dialog box. The observations, it computed itself by, counting what was in the columns and whatnot. And here's our results. This is our test statistic, if you will, right? This is the z-value that we got from the result. And again, how did we get that? Well, if you really want to compute it, I mean, we could do that. I'm going to shy you away from it, but you really want to go back and compute all of this. I'd rather you try and understand it, right? To really understand what's going on here. If we're really not going to compute this, Excel is going to do it for us.
What was the zero on that hypothesize mean?
Well, let's look at the test again. So we're reading this. The manager wants to find out the difference between the mean ages of customers who shop at the two stores. Right? He's not really arguing that there is a difference. He's not arguing that the mean age is less than in the urban store and the suburban store than the other one. He just wants to know, are they different? Are the ages different? He wasn't arguing that there was a direction implied. He wasn't suggesting there was a tail.
People like 5 years or older, there's 5 years between. People in 20 shop at this store, and people in 40 shop at the other store.
Right. If you had an actual prediction, right? If you actually assumed or thought that there was a reason why the average age in one store is less than the average age in another store, you might have that and set your hypothesis up like that. But that's not how this was set up, right? We just want to know what's the difference between, and what is the difference between the two stores, and is it statistically significant, right? We weren't hypothesizing that it was less than in one store or greater than in the other store, right? We were just asking the hypothesis, the null hypothesis for us was, in fact, that the means were equal. So or, right, that's what he's really hypothesizing. However, you can always look at it like this, right? Minus x bars of 2 equals 0. So, right, what did I do? I just subtracted that from both sides of the equality here. Now, here's my difference. I'm predicting that my difference is, in fact, 0. If he had a particular reason to make a prediction on what this difference should be, we could enter that into the dialog box as our hypothesized difference. Okay, but we didn't, right? We had no reason to believe that there was any difference between these two. So I'm the one that entered the 0 in that dialog box. Okay, so we got our test statistic here, and what are we doing? A one-tail test or a two-tail test? Yeah, we're doing a two-tail test, right? This is a two-tail test, so we can literally just come down here and read this. Here's our actual test statistic. Here's our critical, where is it? Our critical two-tail, right? 1.96. And again, this was what we actually got. Here was the critical value. You can pretty much tell that's statistically significant, right? That's way out in one of the tails. This is past the critical value. And the probability of that is 0.015. So we have a statistically significant result. So we are going to reject this hypothesis that the difference is 0. In fact, there is a difference between these two, and you can pretty much see it, right? There it is, 5 years difference. Inner city people, the average was 40, and the suburban shoppers, it was 35. Okay? So again, just think again, how easy was it to run that test, right? The problem isn't going to be running the test. I think in your future, the problem is going to be selecting the test, making sure you have the right test, and then interpreting the test. And I think to make that point, you can run the test before you even figure out your research hypothesis. That's not necessarily a great idea, right? I mean, as a scientist, we would like to set up our hypotheses in advance so we know what we're testing, right? But from a practical standpoint, if you're just eager to get to the results, you could certainly run the test, and then decide, well, what is it I wanted to see here? What are we actually testing? The test doesn't know. It's just giving you all the data, right? It's giving you this. If it was a one-tail, test, it's giving the same things if it's a two-tail test. So we have to figure out what kind of a test that was that we were doing. So with this, we're deciding we're doing a two-tailed test. So we're looking out here for the z value. We get a probability of 0.015. This is less than the 0.05 level of significance, so we in fact would reject this hypothesis. Right? These are not equal; they are different. Okay. So let me go back to the slides for a minute. We didn't have to do all this, right? I mean, I did sort of set this up, showing you, the difference in the mean, but we didn't have to calculate this pooled standard error. We didn't really have to worry too much about this interval estimation at the moment. All we really needed to know was, right, what was the hypothesized mean difference? Was it 0? Was it something else? And we also had to know, right, what our confidence level was. And so we got that from the data. We also did have to know, again, the population standard deviation. But that's why we ran the z-test, right? We were given the standard deviations of those two populations. So we're given that, you need to run the z-test, and we had to turn these standard deviations into variance, which is just squaring the standard deviation. Okay? Again, this is the part I wanted to skip. I think I just will skip it. You can follow along in your book. You can build this template if you want to by following the slides. But my personal impression is it's so much easier just to run the z-test from the data analysis tab, okay, than it is to build the template and start putting things in this particular template.
So is this called the number then?
No, this is just we're still just doing z-test of two samples. Okay. So yeah, we're doing a z-test. Here's a new template, if you will. But again, wasn't it just so much easier just to build this thing in Excel? Right? All we did was paint up the columns, answer a few questions in the dialog box. Right there it was. So going back to the slides, I'm not really going to cover that. You have it if you want to build a template. Okay, but I don't think that's really the way to go. I would not build the template. I would just run the test directly from the data analysis running up on top.
Daryl, would you be so kind and go back to what we just did and kind of help me interpret the numbers?
So you want to see this again as far as building it?
No, just each one. Well, I know what it means.
Okay. The known variance. Let me just bring this up again. Data analysis. I came down here to z-test for the sample means. Okay, so there was a dialog box that we had to complete. Right? I had to paint up, tell it what the one sample mean, where's that located? That's in the A column. Where was the sample mean for the second one located? The B column. Our hypothesized mean difference. Well, we were hypothesizing this, that there was no difference. Right? Okay, we were hypothesizing that this difference here was 0. So I just entered a 0. We had to enter the variance. Again, this was given to us in the problem. That's what allowed us to use this particular dialog box in this particular test. So the known variance, this is really the standard deviation squared. Right? If you didn't like to enter it, didn't want to do the squaring in your head, right? You could certainly enter the 9 and the 10, square them. I click labels here just because, again, if you use the labels in your analysis, well, Excel is going to help you out, and it's going to label the column output for you as well. Right? I didn't type in inner city and suburban. It got it because those are the column headings here, and we told it we were dealing with labels, that there were labels in the first row. I entered the alpha value of 0.05. That was given to us. And the only other thing I did, I clicked output range. I moved over here and said started in D2. So it started printed its dialog box right here in D2. Okay? You don't need a template for this, in other words. Right? If you're testing sample means, you don't really have to go through and build that template that we have in the notes. But if you're much more comfortable with that, you certainly could have done it. Here's the instructions. I know your textbook has it. But I think it's just so much easier to run the actual test itself.
You also gave us the template in that workbook too.
I don't know if I gave you this template. I gave you all those other 3 templates though. But for 2 sample means, I don't know if I gave you a template for that or not. Did I?
Yeah.
Okay.
It's part of that home style.
Oh, okay, that's right. That's right. I did put that in there. Okay. So yeah, you have it then. I couldn't remember if that was just in my template, if that was in my home style or your home style. So I've actually brought up mine. So if I were to bring up your home style.
So there, I have another question. I'm going back to that one.
Yeah, there is a template. Sorry.
How
I
does
just
it look with the distribution method?
How would that look? Okay. Our hypothesis was that our mean difference was 0. Okay. And again, we weren't giving it direction, right? We weren't pointing to a particular tail. So with 95%, with our alpha 5%, then we know that this was going to be 0.025, and over here was going to be 0.025, and this in the middle then would be our 95%. So again, if we got an observation in this range, we're going to accept the null hypothesis. Anything outside the range, we're going to reject. So again, if we want to do this with z values, this is the z value of what? 1.96, and this is minus 1.96 for our z's. And what was our actual test statistic here? Where is it?
Relevable.
Let's go back to the our z value was 2.41. Okay, so we're way out here. 2.41. We're way past 1.96. Okay, so this is statistically significant. That difference is in fact statistically significant.
So are you supposed to be comparing the z's here, or are you supposed to be comparing it against the significance value that you want? Doesn't matter.
So you can compare a z versus z critical value, or you compare your p-value versus your alpha value.
Right.
They're giving the
Doesn't
same
matter.
results.
That's, what we were doing yesterday, talking about whether or not you wanted to do the p-value test or the critical value test. It's exactly, they're going to give you the same results. It's, that decision may depend on what data you have, maybe what you're more comfortable with, right? But that's exactly what you're doing. You're either comparing, right, this z statistic that we computed, our test statistic, with the critical value, or, like you said, we're comparing our p-value with the alpha, against the alpha. Okay, so this is fairly easy to do when you run these analyses here. When you're given the standard deviation and or the variance of of the data when it's known, then this is a very easy test to run, these z-tests. So there's a template. Again, really can go through this, but when you have these, two sample means, if you will, right? You can set up these hypotheses: left tail, right tail, or two tail. Yeah, these are the hypothesized means that we're going to get. We don't know that, but we do know the sample means, right? We actually compute the sample means. That's what we test. Here's our test statistic. And if you really want to look at it, that if we subtracted, one from the other, if we're forecasting some kind or expecting some kind of a difference, then we'd set it up as minus the difference that we are expecting. But we weren't expecting any difference, so here we actually just had this as a 0. Again, just like z, we've got, we're literally taking the difference between, some two observations that we have, and we're dividing it by this notion of standard error. We're asking how many standard errors away from, how many standard errors is this difference? Just like we did with z tables and like we did yesterday as well. So we would conclude using alpha 0.25 thought we were using 0.05. Oh, this is a new problem. So can we conclude if alpha was 0.25 that the mean age of the customers is store 1 is greater than that of store 2? Okay, so now we're looking at a slightly different test here, right? We're taking this and we're suggesting that our null hypothesis is that this difference here, right? There is a difference between store 1 and store 2. And that, like I said, customers of store 1 is greater, they're older than customers of store 2. So we could use the same test statistics that we did. I've already done this. Right here is the template, and this is the output. We can change our alpha value here from 0.05 to 0.25. Okay, so I'll run another test. We'll do data analysis. And now we're asking at 0.025. Put it down here.
Did you change the alpha?
I didn't change anything. I changed the alpha. Right, I changed the alpha to 0.025. Yeah, what effect did that have, really? Well, you can see that some of these critical values changed, right? Here was our z value for critical one-tailed test was the 0.64, 0.645. So we changed it to 0.025. That changed our critical z value to 1.95, right? But notice the probabilities, right? The p-values didn't change at all, right? We got the same p-values as we got before. All that really changed was the critical z values here. We got the exact same p-value here for both the two-tailed test and the one-tailed test, two-tail, one-tail, right? All that really changed here. Our z statistic was the same. Nothing changed the data. It was just the critical values that changed. We could have answered this, right, without even running it again, right? Because we knew what the p-value was. And what would we conclude here? Are these differences significant? Is this one-tailed test? Is that a one-tailed test? No, it's just a two-tailed test. Is it significant? It's the same p-values, right? Here's our p-value from two-tailed test. It's the exact same p-value, right? Up here doesn't matter. And so we make the same conclusion, even though it's a more stringent test. We would still reject the null hypothesis.
Isn't your z different?
Critical z, not the test statistic, right? The formulas we would use to compute the test statistics, that hasn't changed at all. So we got the same test, the same z test statistic here. What changed was the critical z's, right? Our observation was the same, but the critical z values changed because we were making this more of a stringent test now.
We made alpha like 0.01, we may not be able to test it in 1 second.
That's right. If we made alpha, right, if we were to run it at 0.01, you can even see some results. It would not be critical. Let's just do it for the heck of it. So I'll make this 0.01.
I was trying to compare the top and the bottom one.
I'm not going to help you much. Right, so now I just ran another one here. We're going to get the same, some of the same values here, right? Here's our z statistic, our test statistic again. Didn't change. Our data didn't change. Nothing changed with that, right? We have the same variance, same standard errors. Everything's the same here. We got the same z values. We didn't change the data. Got the same results. What changed were these critical t values. So if we're doing a two-tailed test, right? We're doing this test right here, saying that there's no difference between the means. This is a two-tailed test. Here's our critical two-tailed z-value requirement, 2.57, and what did we get? 2.41. So we failed to reject the null hypothesis. Yeah. And if you wanted, again, we didn't even need. You could have just looked right at the probability here. The probability of two-tailed test is actually greater than 0.01. So we didn't even need to run it. You can look at the p-value to figure out whether or not this was significant or not. Okay?
So, why didn't the value change? So if you're trying to look at the numbers and what to compare in that table to see whether it failed or passed.
Sure. Yeah, the only thing that changed.
You're not looking at the P's anymore, because P's are exactly.
Yeah, P's are exactly the same, right? That p-value came from actually the test data and the test statistic, right? That didn't change at all. Here's our test statistic. That's going to give us the p-value. So that didn't change. Got the same test statistic. We got the exact same p-values here, right, for both the one-tail and two-tail test. What changed were when we changed this, right, from 0.025% or 95%, now we're out here at 99%, right? We're saying 0.01, sorry, this becomes 99%. And we move this out here, so this is 0.005. And it's 0.005. Okay, so we really just moved these, right? We moved our critical values out a little bit further. So we want to be more certain, right, before we reject the null hypothesis. So that's what changed. The data itself, nothing changed in the data. We still have the same means, the same variances and everything, right? We still have the same hypothesized difference. The test statistic was the same. The only thing that changed were these critical values for the one-tail and two-tail test. And so if we're going to compare, here's the one we observed. That's what we actually got from the data. We're comparing it to this critical two-tailed test, and it's not sufficient to reject. Right?
In this table, you have to look at the Z's. You can't look at the P's because you don't know unless you remember what your significance value was. The kind just shows it to you on the table, and you can look at it and go, oh, this is this. You have to
No, you can look right at it. You can look at it. You can write it. Here's the p-value. Where's it for the two-tailed test? Right here. You can look at it. It was the same up here. It was the same in the first one we did. Right? We got a p-value of 0.015. That is not less, right? We're asking the question, is that 0.015 less than or equal to 0.01?
Right.
No.
It's not in the table, I guess is what I'm saying. 2.41 is in the table. I can look at 2.41, look at 2.57 and say, okay, that's either in or it's out and make a determination. The other number, your 0.15, is not in this table. So you have to remember that and look at that and compare it that way.
But it'll be part of your question, though.
Yeah, you'll actually know. We're going to tell you what the significance level is that we want for the test. We were just changing it along the way. And again, nothing really changed except the critical.
Right, but looking at that table, I can't remember what we did between the tables.
Yeah.
I guess that's my point. I can look at the Z value and make a determination.
Okay. Yeah, you can look at the Z values or you can look at the P values. You still have to make your hypotheses, right? I mean, that's the one thing about this, cell. It's going to give you the test statistic and the result, but interpreting it's going to be the challenge, right? But actually getting this, there's nothing to it, right? We're just taking up the ranges. We had to make a couple decisions here, right? The hypothesized mean difference and what the variance was, right? The known variance, but once you just keep those terms in, so. Right.
And why you said lowering the alpha number instead of the I?
Well, just to show you, we had a question, right? That, would it be significant at this level? The next level would it be more significant, right? If we kept making the test more and more stringent, and I was making the argument all along, you really don't need to run the test again, right? You can look at any of these outputs and you can see what, whether or not it would be significant at what level. You didn't really need to run it again. I just did, right? Just to show you that what changes is, the changes are these critical values, right? The critical values, not the actual Z. This Z is our test statistic, right? This is what we would get if we go back and use those formulas and plug in all the values and do all those computations. That's what we would get for Z value. What do we need to reject the null? We need a Z value down here to reject it, okay? I'm more of a p-value guy myself. I don't know. Matt, what are you? P-value, critical Z's?
P-values are the easiest ones to remember, easiest tests to do. P-values.
That's a p-value too.
So I did give you that template in the home style example if you want it. But frankly, I think this is so much easier just running just running the Z test like that. Okay? All right, why don't we take a break and we'll come back, hammer some more here. This is what we're gonna do next. We're gonna look at, again, we're gonna take samples from two different samples here, and we're gonna test whether or not we get differences. But here, we're not going to know what the standard deviations are, the population standard deviation. So look at my little table over here, right? When the standard deviation is unknown, where you have two sample means, you probably want to do a t-test, which is exactly what we're building up to do here again. Okay? Again, don't memorize the formulas. Don't worry about the formulas. We'll get through them really easy. Let's take a break and we'll come back.
I know, so I'm like, I'm exhausted. Oh my gosh, that was hysterical, Sean's comment. Oh my gosh.
I think it's just more hysterical coming from Sean.
That's exactly right, you're exactly right.
Yeah.
Yes. I was like, can you just say that? He said, yeah, thank you. It's on Brute Me. It's on Brute Me. He said, rock out with your cock out. I guess it goes from a movie, but I don't know that. I was like, you have to go on Brute Me and look at the conversation. Alright, I need a break in this thing.
Tucked it in, I'm not sure why. You take it off or tuck it in?
But you ought to use
How do you tell the difference?
But yeah, then you ignore
They don't have to worry about that one.
So one going down the left, one down the right.
What is wrong with
Yeah, that's why I put that on the board, because I think that's really sort of the crux of it. That's what you guys are really trying to figure out. What kind of a test we just use that little chart over there, and I swear it's going to be probably yeah, that's what we're really talking about. And then there, if we find an exception along the way, I'll let you know. But I think everything we're
With this.
But your exception, again, the reason you don't want to use a t-test is because
My false statement is
standard
going
deviation is different. And you could do it, and on this, you really could, right? You would want to, because you test that.
So I only do it.
Yeah, you have to use it, right? But you don't have to compute it. It'd be like ignoring it. That's the argument I make. Now, if they don't give you the population, the standard deviation is a choice. Excel's going to compute the sample standard deviations and use that as predictors for the population. But if you already have predicted, then yeah. But that's what it is. It's never said, it really is. Oh, yeah. And it's going to get easier from today forward because it's so much easier to set up. Really, like you saw what we did here. We just literally, there's a data with two columns, painted it up, pushed a couple buttons, click, there's your answer. Didn't have to compute anything. Right.
Oh, you do like I see. And you did them in. That's why you should.
Right. So I just take care of us.
We're going to do a lot more today. Yeah, that's why I was trying to give you some table over there. Yeah.
When we ask a question, where do I look?
Always going to lower.
And I may not have given you all the information of those couple problems. I just made them up this morning. I had the actual data, right? That we all had access to this data, and they actually come with a smarter question in the back of the textbook. But I didn't want to use the question. I just wanted to use their data. So I wrote the questions and stuff. So I had data.
And this, I know I do.
Well, think of that little table over there. That's really going to help.
Or two tail. You would never consider an upper tail.
Yeah.
When they're looking at something.
I like to do more practice and less lecture, my goal. I'm really trying to do that, but unfortunately we do have to. Yeah, I'd rather not. I'd rather.
Smaller version, smaller value and one of the two single tails, that's the one that would drive out.
Okay, so what if you're doing? Oh, I see. So if you put in two, then it will just.
So if I put in 2, and it just was the 2 value compares significance and 2 value rejected. So
We'll
Getting it?
build more formulas in.
I'm making a good template. All I need is the 1 or 2 tail answer, and then the significance value. And then
Yeah,
Just tells you the answer, reject or.
yeah, p-value, I mean,
Are you feeling it?
to me, that's just the easiest
Yeah,
number to
I'm
look at, because then you look at the data and you confront your level of significance versus p-value, and you make a decision. The critical, Z's and all that, yeah, they're fine, but you still have to.
Just.
I know. And then all these kids are not, oh, yeah.
Yeah, that's not gonna be able to answer all your questions, but that'll help you a little bit.
Right, well, we were just building more formulas into it to actually, based on the test statistics,
Ah.
the alpha, check with if statements, saying if this is that, then reject. Or,
Yeah, you could do that, you could literally build a little formula right off the alpha, right? It's gonna give you the answer, right? Yeah.
yeah,
me messing up, interpreting the value, and all I have to really think about is a 1 tail or 2 tail test. That's all I need to do.
Yeah. And again, hopefully, nobody's out here to trick you with that, whether or not it's a 1 tail and 2 tail test. It's,
Adding about 50 at this point.
no, I get it, but it's literally for us to claim it's a 1 tail test, there's gonna be some prediction that something is more or less than another, not simply that they're not
I don't
equal.
mind crapping all, I don't mind being crapping.
And frankly, I'll be honest, I do not do a 1 tail test too often. But I know they exist, maybe it's just not my world that I don't do them. I know they exist.
Whenever you're with someone,
But you have to have some notion of that direction. Why is that less or greater? Why you have some theory to believe why it's greater? Like that example with the university baby.
When I started.
Well, the dean wanted, that's what he wanted to know. He wanted to know, our business students, are they achieving less than the university? Well, that gave you a big hint, right? You didn't say equal, you didn't say different, you said less. Problem said less. So if you see that, something about less than or greater than, you pretty much know it's gonna be a 1 tail.
And it's the same all, and I always have all
Again,
this cat in my head.
My helpful hint on that, I don't know if that would be, but I would, when you think about these four hypotheses, if you have a 1 tail test, I like to think that the alternative, that the inequality is pointing to the tail of interest. Right, that's gonna show you, if you want an upper tail and a lower tail, right, that inequality in an alternative hypothesis is pointing to which tail is gonna give you that test.
Right, but we see that when we do both. When you calculate the p-value, both the upper and lower. Those are hybrid.
Exactly.
I can't do variance for really large.
Right, exactly. You can bring up that test.
I don't know, like, the difference in the swing like a dry ice can, minus sales.
I got my driver, like, at least I've got my driver down for one base, like, it's not. My miss is up. I've got to slice out. I'm the same way. It's, if I get tired, I start going through with my arms, my body's not following through. That's all I know. I gotta just slow down.
Mine's
You have a fade? Those are tough to get rid of, man.
and then like we play this one course.
Close your face.
Eagle Crest all the time. And on 18 at Eagle Crest, you're supposed to hit it kind of down a hill and it drops off. I always end up on the fairway of the other hole. Every single time. I can't stop it.
There's one at a mountain course in my park. There's a couple where my hook will end up on the other fairway.
Sometimes you have a draw, a bad hook.
Yeah,
Snap hook.
my miss is a hook too. If I get too fast. Kind of blocked out the slides. I got that eliminated.
Yeah, I had a slice of a fade for years, and it's taken me years and years to get over that fade. I would love to be able to hit a draw, but I only get them every so often.
The worst about my least favorite hole in mountain is the par 3 where it's just like Just right in front of just the green.
Yep.
I don't know.
Sure,
why,
but
right?
it's a huge.
It's a huge big gap. I think about it too long, and I'm always like, oh, I'm afraid I'm gonna get over it. I'm like, just get over it.
Oh, yeah.
Yeah. Just hit a wedge. It's always like, if I hit, I always try to hit my seam. I always think, hit my seam. There's hit my pitching wedge. Pitching wedge.
Oh, is that? I'll check perfect on that.
Yeah, that one. It's a huge number of those. The other one is there's a par 5 on the back.
Without them, we typically, the assumption is, it's generally, alpha equals. This is general.
And I'm almost like.
But if you, again, in the medical community, maybe you want to have an alpha.
Then it's that second.
Yeah, that would, you know, one word, alpha equals one. Oh, here you go, this, it is 99, so here's Detroit 01, takes off like 99%. But so over here, somewhere over here, this is like top so many balls into that stupid. Oh, in the area. Wow. And our Z values, right? But our Z values will be small too. This is 1.96, and over here it's 0.1. I used to know this. I just know this. No, it's actually little. Oh, right, yeah. Yeah, no, I know. I all this. This was the, yeah, these were just, I actually just sort of built these this morning. If you open up your quality, you're only going to get the column. And I just wanted to make a problem. I didn't know how to give you guys. I just wrote that this morning. This is
I did my 5 yesterday.
I should have given you. I was just trying to get you to run this test. I took these 3, they're all of these have.
Utah didn't beat.
You got salary, you're gonna spend journalism. Don't let it get you. Not everybody knows. That's bad. I was sometimes yourself to get a different perspective on this. It's trying to explain that one issue, why we had to multiply this p value to get to that. I struggle with that myself, and I understood it, but I realized that's guys. You never necessarily even have to settle it.
I don't know.
So let's say we have some numbers. Okay, we got some numbers. If you, this is one of the examples. Equals. Equals min. Okay. Yeah, that's minimum. So literally just here we go, making up the range, closing it, and trying to find that total amount. You can also do, there's also a difference max. So max, they paid out the numbers.
I talk about you guys a lot.
Right. So here, the reason we were doing this, the reason the template does it, is you clearly can't take and double that. Right? You have a problem. This is probability. Probability. Over one, we can't have probabilities that are greater than one. Right? So, you know, not knowing in advance which tail we will be the lower tail, and we just go, but we're going to take the lower tail, i.e. the middle, which is the lower. Well, okay, but what if you could do that? You could just say that one times two. But what if you then got a different test statistic where these numbers will reverse, right? So it was just handy, the designer did that, just kind of handy saying, well, I know that I'm going to take one of those values. It's always going to be the small, right? You didn't know if it's going to be in the lower tail or the upper tail. It could have been an either tail. Yeah, you're right. We're multiplying it because so hard to explain that. If you're going to do one tail, right? You're putting all of that in
This guy has every
0.05.
single girl.
Just think about that critical value.
I had to point it out. No false advertising. No false advertising.
I know, I was really ashamed of myself when I went to that.
Now you've got both of these areas. And we're not changing. Here's the, I think the problem is, although this is, C-test and whatnot, what we're actually getting to is some Z-test statistics. This is where we get these things. Okay, that's not changing. But all of a sudden, the area is double. What? That's why the p-value. Because all of a sudden, you know, this critical test statistic is seen to be computed, not from the table. We actually computed it from the data, by taking, the mean, hypothesize, divided by standard error. That isn't going to change. We've still got the exact same Z value. This is 1.53 or something. Example. Okay, that doesn't change. Regardless of us changing the level of significance. Eric's, doesn't change anything here, right? This has no alpha term, right? Our alpha
Proud of yourself in Excel.
our alpha is 2.05. Well, yeah, no matter, right? So that's not part of this formula. That's not part of our Z as statistic, right? So that's not going to change. But what's changing all of a sudden is no matter what you take that around. Saturday. Probability. I think it's this way. The next material here probability. Oh, okay. So, my first saw it. Yeah, we're actually doing it because even though we're talking about Z values here, like the table, no, I was actually there was a very much Z stat. Z stat, which is test. Oh, nice. Okay, that's our test. So that's based on the data. Okay.
Yeah, I mean, like I said,
the p-values are based on the data. But the critical, alpha, where we draw these critical Z, that's just based on the alpha. The same alpha. I have never dash out. I've always got rid of it.
But it's not option.
No, a couple razors. No, I know somebody don't know that. Don't worry about it. No, one thing you can get out of the class. Right. It's not true. It's not true.
I think we go take pictures of people casually talking in costume.
Yeah.
Oh, I can't.
You could. You're really not far from doing that. You're ready to do it now. You already know how to run the test. It's all going to be about the interpretation, okay? But I would just tell you this, right? Just look at these people. And if we're talking about confidence level 0.05, all you're really doing is comparing the p-value to which is killing me because it's less than 0.05, greater than 0.05, it's only greater. So our analysis here, we're doing 0.05, two-tailed test. We're going to reject it. We're going to no, just assume we're doing a two-tailed test. If we're doing a one-tailed test, yeah, we focus on this. We have the same question, is this less than alpha? And the question is, is that less than alpha? We would reject, both of these we would reject. Remember, that goes on all of my devices, so my mom gets on. Well, no, that's.
Okay, you got it.
Usually we have this upper tail is.
We haven't set up that.
Yeah, if we're doing a one-tailed test, all of this area. So that's why you get such a large number. Okay, so we're doing if we were doing an upper tail test, and then which area is this? But we weren't really doing it.
I mean, you have
Which again, remember this, right? That's this.
wasn't me.
So this is going to be one of these numbers is all going to be.
He's a resident right now.
So but again, this is not, you know, these are going to, I can point to the right, to the right test.
So it's also saying that.
It is. So we're rejecting it. So that's what makes it statistically significant. Remember, our null hypothesis. H2O, right. Hypothesis stuff. In this case, they should saw it off at two different ways. That, but the mean difference.
They actually know how like have most of this from zero. It's pretty good. I stuffed it open. To him and his arm.
The alternative is
just nudge so I can see.
that's not even
It's like
not
all I
even.
did is just
But again, this is one
like okay. So my brother
if it was predicting something, let's just say for some reason you have some mistake. So I explore these differences to solve this. And 5 years, like stops. And so then we're predicting this difference. So here we look at this. That's the way house is like now for find out whenever you look, it's like yeah, not. It's like yeah, somebody's that car. Expected to just I was like, Anthony, I don't think this rule works. I don't know.
Should we get him in?
Yeah.
Stats, guys. Come on, hurry. Stats. Erickson here.
Now I know.
How's it going?
This one's done. I'm just going the other way. Eric.
Oh, man. This
Okay.
is my,
I just kept on going down. Oh, you should show this in the first one. Wait.
Now I get it. Now I get it.
Oh, let's take, oh, wait.
Now it makes sense.
Why? You put it out here. Here you are, Eric.
Cortex
Yeah.
one.
We have to take it, right?
They actually gave you guidelines.
Yeah, no, so that's why we were, just so you know, like.
Wait, is this your?
Yep.
Oh no, these are yours.
So me and Nate pulled that plan. Why was it crazy? Isn't that crazy?
We didn't get any
So
money.
either we were just saying, like, that's why it was like, so.
Yeah. So they, and the whole thing is like, you basically weren't solving any problem.
Oh, I already got
What you're allowed.
yeah.
But
Yeah, that's why.
Oh, yes, thank you. Wait, I was here. Let me take a picture of this.
Wait, what?
I haven't watched it. I'll watch it before tonight.
I mean, not there, Larry, it's hysterical.
I will watch. I'll watch it. So you're going to the same
It's
time.
on some
It's from like an Aussie guy.
So, yeah, to go to my little table over here,
Nazi
we're
bloke.
talking about running a test when we don't know the population standard deviation. And we're probably gonna do some two samples soon, so this is really pointing you to t-test. I thought that was fully simple, Again, I'm not gonna go through all these formulas, just, if you wanna get a sense for them again, what are we talking about? We're looking about the difference between two sample means, and we're asking, is that difference significant? This is gonna give us some sort of interval estimate, if you will. We take the alpha divided by 2, so we're splitting up alpha on both sides of the tail, if you will. Interpret this as like, again, the pooled standard error. That's what we're really sort of doing, right? We're taking the standard deviation, actually it's the variance, from each of our samples, dividing it by the n, right, the number of observations. So, think of it as like this sort of pooled standard error, if you will, right? We're using both the standard deviations or variances from both our samples to compute the, that pooled standard error. Where the degrees of freedom are, you don't have to calculate any of this, okay? You really don't have to do this, but if you're really curious, if you're really interested, right, this is how you could go about getting the degrees of freedom. But isn't it so much easier just to get it from the test itself rather than have to do all this? Okay? So there's our test statistic again. And it's just like we've been doing before when we did Z's, right? We're looking at the difference between two sample means. Okay, we're dividing it. In this case, we allow for this difference. If we're predicting some kind of a difference, we can take that into account too. We get this difference and we divide it by the standard error. And we're trying to understand how many standard errors is this difference, right? How many standard errors does that really account for? Our test hypotheses, again, might be something like that. That the difference is between these two is less than or equal to 0 or greater than 0. If we have some sort of an actual prediction here that there is going to be a difference. So how do we do this? Again, let's open the data file. I'll leave this up here for a minute. We can see what's important to us. Analyzing new software, packaging, reduce the time to design an information system. So we have 12 analysts asked to use the software, another 12 were asked to use an existing technology. We're setting alpha at 0.05. Okay, and we're going to run this statistical test where here's the mean time using the old system and here's the mean time using the new system. Again, our samples, though, are not, right, they are the point predictors for the population values here. So open up the software test data.
So I just want to make sure. Chris didn't make it tonight, did she? Okay, good. I want to make sure. I'm not good, but I do want to make sure because Chris is like, what kind of way?
So that's what we got, right? No template. What are we going to do? We're going to do a t-test and look at our choices here. We have 3 choices. Okay? Paired 2 sample for means. This is not a paired sample, right? These were a different set of 12 software people, and each of these were not paired up. Okay, if this was, this would be a paired test if we perhaps had the same 12 analysts. One time they use the current system, the next time they use the new. That's not how the data is. The data that they collected had 2 different samples here, so we're gonna come down here and we're gonna click on this next to last one, 2 samples assuming unequal variances. Yeah, this is more of the safer option, if you will. Again, what do we do? Well, here's the current. Here's one variable. Oops. And here it is for the second. Oops. Hypothesized mean difference, let's assume that's 0. We have labels. And what was our alpha value here?
5%.
5%. So we'll say 0.05. And we have to tell it where to put the output. How about right there? And so this is, I think this is the kind of test that you might find most often in sort of your normal work, right? If you're taking samples, 2 different samples, you're trying to compare, the results from 2 different samples. So what did Excel give us here? Well, it computed the mean of each of those samples. It computed the variance for us. It counted the number of observations. And it gave us a t-statistic. Again, what are we doing? Are we doing a one-tailed test, upper tail, lower tail, or are we doing a 2-tailed test?
One tail.
We're doing a 2-tailed test, right? We didn't have any specific, argument that one is faster than the other one. And you can make that argument. They're hoping that the new technology is in fact better, but you don't want to make that hypothesis. We'll just assume they're the same. And so we're using a 2-tailed test. For a 2-tailed test is 0.03. So what do? Accept or reject the null? We reject, right? So it's, again, the way you can interpret the p-value is, what's the probability of getting this result if it was just due to random chance? All right, and this is saying there's only a 3% chance that you would get this result if it was just due to random chance. There must be something there, right? There must be an actual difference between the current and the new. Okay? So, with a 2-tailed test, we would in fact reject the null hypothesis, and we would now assume that the new test is in fact better. Just another comment: why wouldn't we want to, make a one-tailed test? Back to what Matt and I argued earlier, right? This is a more stringent test. Right? Using a 2-tailed test is going to be more difficult to actually pass, to find significance. And if we're talking about some major change in our business systems, we want to be pretty sure, right? Let's make sure it passes a real strong, stringent test. Okay?
That's the question.
Yeah.
Do that again, but actually just do the areas and not the overlay. I came up with a different number. I did it. No, delete it. Leave it in there.
Sorry, I thought you wanted me to run the thing again.
No, Control Z. Show it in there. Leave it in there. Damn it.
That's all right. I got it. Now we want? Oh! I have no idea.
Break it.
No, you didn't have to do this. I'm not sure. Just go off every now and then.
I didn't do it.
Give it a second. Just trying.
Control V again.
No, I actually did hit Control Z, so I just did the back.
Control Y. Undo. Redo.
Yeah, I'm not a technology. Is that thing running, Matt? Yeah. It's trying over here. It's just flashing off. This thing needs some work.
This is the time.
This is where it's at.
Oh, labels, yeah.
I don't know.
Not wait a minute.
Oh, it's close like whatever. So, now like
Probably
whatever
should
we
be-
are
Yeah.
it's not worth it. So it's not worth it.
Yeah, I've seen that before.
The likelihood of retention is.
But
I don't know how often they change their lights and stuff.
I selected the area, but I think
My wife made that. My wife made it.
She
Made that out.
Is that it making the noise? Is that it making the noise?
Wow, that was loud.
Yeah, that fan might be going bad. If the fan goes bad, the bulb goes bad.
That's a pretty weak ass display, isn't it?
He said ass display. Don't let Eric hear that.
Yeah, seriously.
Okay, I don't know how that happened, but Jen, it wasn't you.
I'm gonna get blamed though by everybody.
Oh, yeah.
Oh, yeah. They were both like that. Yeah, I got nervous because I was like, oh my God.
So again, this was this was the problem, if you will, so we're asking you to do. So you took the data, right? These were our test hypotheses. We set it up, we ran the test, and again, you can run these tests without even knowing what your hypotheses are. I'm not recommending it, but it's going to give you all the information you need. And then, you have to decide, are we doing a one-tailed test or a two-tailed test? Actually, it was a one-tailed test. I can't remember the problem. All right. So, again, hopefully we all got the same numbers here. So, do we accept or reject? Right? Man, the probability is what I look at. Did this happen just due to random chance? No. If it's greater than 5%, we're accepting that, well, maybe this was just due to some random variation in chance. But when it's, our confidence level of 5%, we're talking about that is less than 5%, so it's statistically significant. We reject the null and we accept the fact that these sample means are not the same. Okay, clearly, the new one is better. Now, let's talk max samples. Okay, the test is going to be the same again, right? But we're actually matching up the rows. They're coming from the sort of the same element, if you will. Here's some statistics. This is how we're going to compute the mean difference, if you will. There's the standard deviations again, the t-statistic. So let's try this matched data set for a minute. We can actually talk about that. Let's just look at the problem first. So we've got 6 workers. They each use 2 different methods. Okay. So in the previous problem, we had an n of 12 for each of the samples, but it was 12 different people in each of the samples. Now we have 6 workers, and they're literally in both of the samples, and they're matched up. They're not just randomly put together, but they're matched up. So we're going to get the matched data set. Where the heck is it? Oh, thank you. Okay, so let's look at the data, right? Worker 1 did both methods, scored a 6 and a 5.4, the same thing with worker 2, right? these belong to, these scores each belong to one of these workers, okay? So we're gonna run the same kind of a test. We're gonna do data, we're gonna do our t-test, but now we're going to do the paired test because these observations are paired together. They belong to the same workers, okay? So this is the test we're going to select. Paired. Click OK. The rest of it's going to look identical. Here's our input 1 range for variable 2. Hypothesized difference again was 0. I'm going to click the labels. So we want to use the labels for our output. 0.05 is level of significance. I guess that was correct. Is that right? Is that what we wanted? 0.05 level of significance. And we have to tell it where we want the output. We'll say right there. Like that, right there. Okay. So again, this table is going to look identical to the other table. So method 1, the mean was 6.1. Method 2 was 5.8. Calculated the variances for us. Even gave us a correlation coefficient. So this is really suggesting that there is a high correlation between these methods when we control for the worker. So degrees of freedom, right? You should recognize the degrees of freedom, right? It's n minus 1. We had 6 observations, so our degrees of freedom is going to be 5. It computed the t-statistic for us, right? And we have a critical t-value. We have p-values. So if we're doing a two-tailed test, do we accept or reject the null? We're going to accept. So there's the p-value. Right, the p-value is 0.079, so that is greater than 0.05, so we're going to accept the null. And the other way you could look at it, we could also compare the t-statistic to the critical t-value for two-tailed tests, get the exact same result. Right, this is less than the critical value for the t-statistic, so we in fact accept the null in either of those cases. So yeah, the difference between this test and the one we ran earlier was simply that the samples were paired up, right? They came from sort of the same entity, the same person, if you will, who had multiple tests here. So it's you know, these statistics are computed slightly different, okay? But all we need to know at this point is they're from the exact same. We want to do a matched or a paired t-test here.
So the question was whether or not the new software reduces the time.
So does the new software reduce the time?
No.
Not statistically significant. That difference is not statistically significant. Right. But again, I mean, if you're a business person and you saw these results of 6.1 and 5.8, wouldn't you be tempted maybe to run a larger sample? Right? I mean, we only have a sample here of 6 workers, for God's sakes, right? If we were to run this again, I'm not saying we necessarily should do this. You should design the test to begin with to have a larger sample. But, you know, this might be indicative that maybe there is a difference here that's worth looking at. But again, the difference is not statistically significant. With a larger sample, it might be, but we might get completely different results too. Okay, a sample of 6, that's very small. And what's our recommendation for sample size? When in doubt, what do you choose?
30.
Yeah, try and do 30, right? Try and do 30 if you can. Maybe you couldn't. Maybe you don't have 30 different workers. Maybe that's all they had. But you have that opportunity, you certainly want to do it. Again, you can follow this on the PowerPoints, if you will. This is exactly what I did. I ran the paired t-test here. Same results. Just explaining again. If you want to see, you know, what are we talking about here for I guess this was a one-tail test. I didn't pick that up. Was it a two-tail? Oh, 0.05, sorry. I'm gonna start wearing glasses. Okay. So let's go back here to what have we done again? Now we've done this, right? We've compared two sample means, and we even had another example where we had matched pairs. But again, t-test, right? Because we were dealing with two sample means and we didn't know the underlying standard deviation. So now we're going to get into ANOVA. That'll finish out this chapter, and then the next chapter in our textbook is all about chi-square. But ANOVA, I'll tell you what, I use a lot of ANOVA. In experimental work, I mean, this is just sort of the mainstay of the tests that we do. I don't do a lot of regressions. We tend to do run experiments, so we get different means from different treatments, more than two sometimes, so we're interested in trying to analyze our differences using ANOVA. So again, what is ANOVA really testing for? Okay, 3 or more populations. And again, it stands for analysis variance. That's what it's for. And we're literally testing for more than 2, 3 or more different means. And our test result is going to simply suggest if these means are the same or if they're different. It's not going to tell us which mean is higher or lower, or what caused this result to be significant. We're really going to have to focus some of this on the post hoc test. And I said this is the subject of future EMBA courses. We're not going to run these tests, Tukey, Bonferroni, and Chevy. We're just not going to run them. You can't run them in Excel. You would have to use a separate statistics package to run those tests. Okay, we're not, the only thing we're using here is Excel. But in your work, we use, do you guys even have access to those stats packages, SAS, SPSS? There's Stata. What do you like, Stata? You're probably a Stata guy, right?
I like Stata, but I work in SAS.
SAS? I'm sort of an SPSS guy just because it's a lot friendlier to use. And some of that SAS is probably the most powerful. Stata is supposed to be really friendly to use too. But we get stuck in our paradigms. You learn one software package, you don't want to learn another. But again, these kinds of tests would really examine the particular differences between the means and maybe point out, if you have 3 or more means, is it 1 or 2 of these that are really causing the differences? We have tests to really conclude that. But as far as our concern with ANOVA, we're just going to give you the basics with ANOVA, and we're going to look at whether or not these 3 or more sample means are in fact different. And here's some assumptions. We wouldn't be too worried about this, but let's make sure we understand. Let's make sure that we meet these assumptions. The response variable is normally distributed, right? It's an important assumption. We sort of make everything we do here is with the normal distribution and whatnot. So we're sort of assuming that the results we're getting are normally distributed, and that the variance of the response variables is the same across the populations. Okay. And again, that's something that we can check. And the observations obviously must be independent from each other as well. So again, what are we really looking at here? Well, this is our normal curve, and we get the means that are fairly close to one another, right, from these 3 or more samples, then we're going to say that's not statistically significant. If our sample means, in fact, are hugely different, right, and the ANOVA result may come out and say that we need to reject the null hypothesis that the means are the same. And you'd look at this, and I know you'd be tempted to conclude that it's this one that's really causing the problems, right? This is the one that's really different than the other 2. It's probably true, but we really don't know unless we run the additional tests. And we're not going to run those additional tests in Excel, right? It's sort of obvious that it's this one out here that's really a lot different than these 2. But again, this is what these supplemental tests actually show us. Now let me just show you where we're going with this for a minute. I'm going to back up. I've got a lot of calculations here, but what we're really trying to get to is this ANOVA table. Okay? And I have a comment here. You'll see this in future MBA courses and most software packages. Almost any software package that I run, they will give you this as your ANOVA table. It's also going to be very similar if you run multiple regressions. You're going to start to see this table over and over and over again. Okay? And again, we're going to run the test. Boom, we're going to get this table, and we're going to have to interpret the result by looking at this table. Just like we were doing recently, earlier this afternoon. It's very easy to run the test. The difficulty is, can you interpret this? Okay? And the answer to whether or not these things are significant is actually going to be found in this p-value, just like we've been doing all along. Is that a bingo today? Is p-value bingo? All right. So again, I sort of put this together just so you can see, how these things are calculated. A good economist might actually, he's teaching class, might actually have you build this by hand just to make sure you truly understand what goes into this, but I'm not going to have you do that, okay? I just want to point out, you're going to see this over and over and over again, okay? And this concept of ANOVA, right? We're talking about analysis of variance, all right? We're looking at all the variance there is in the data, right? And we're going to try and capture, well, how much is that due to the difference in the needs? Or how much is that due to just random fluctuation? That's what this error term sort of suggests, right? All of the data we've looked at so far has had variation, right? Even the sample data. So here what we're trying to really understand is it really due to these means? Is, these 3 or more sample means, is that really explaining a lot of this variance? So we're going to take that variance, the analysis of variance, we're going to partition it. We're going to say, how much of it is due to the actual treatments, the means themselves? How much of that is just due to random variation, so the other random variation? And that's how we're going to do it, right? We could look at all of the data, and we could compute the total amount of variance we have in that data. That's what the total is. Some of that can be explained by these means, the fact that we have 3 or more different groupings. Some of it cannot be. Well, if a lot of it can be explained by these different means, then we're going to get a significant result here for this notion of treatment. Because it's the actual means, the actual treatments are in fact explaining a lot of this overall total sum of squares that we see. And remember, sum of squares, if you remember back to day 1, we didn't actually compute any variance. We just sort of accepted it. But you can look in the book. How do you compute a variance? You take the sum of the squared differences. Yeah.
When you say treatment, what do you mean by treatment? Like, what does that mean?
Well, imagine. So I'll give you my world, for example. I ran an experiment where we have one group. We had no information about how they were making decisions and feedback. We had another group over here where we gave partial information, and we got a mean. And then we had a third group over here where we had full information. Feedback, whatever, about the kind of information they were getting. So we had 30 subjects here, 30 subjects here, 30 subjects here. We collected some data, and we want to see, well, is giving people information, does it somehow alter their decisions? We hope it does. We really don't know. But our null hypothesis is, no, these means are going to be the same, right? That's our null hypothesis. So what do? We ran an experiment with, in each case, we had n equals to 30. So I had 30 observations here, and the ANOVA then is going to clearly answer the question, well, the variance you're seeing in the data, is it due to the fact that these observations came from 3 different treatments? Or did it just come because there's just a lot of variance in the data to begin with? Okay, so that's sort of why they call it treatments. I mean, a lot of this comes from, a psychological, medical background where there are actual treatments, right? You give some people this drug, other people that drug. Some people get a placebo, right? A control group. So that's what we're really talking about treatments. You can sort of think about it as an actual treatment, right? In some cases, we're not really messing with anybody. It could be that our treatments are maybe 3 different geographic locations, right? You might look at, if you're a gaming company, we got gaming people here, right? You might have different means from 3 different operations outside of Las Vegas. And you're asking the question, well, am I getting differences in my measures here across these three different treatments? So again, I'm going to back up here. This ANOVA table, I mean, you're going to see it over and over again, not just with ANOVA. When we get into regression, you're going to see the same thing. Okay, even a bit more, built onto it. As we make these problems more and more difficult with more, variables and attributes, the table gets a little bit bigger. But this is sort of the crux of the table, if you will. Okay, we're taking the sum of the squared deviations. I've got an example here to show you. Right, we're trying to partition that variance. Is it due to the treatments, or is it just due to just general error? Okay, and if it's due to the treatments, then we're going to suggest this is significant. So let me just go back a little bit. Again, if you really want to see this, then just following along in the book here. I'm not really going to go through it. Here's how you compute the sample mean for one of these treatments, right? This is the sum of all of the variables for this particular treatment divided by the number of observations. The sample variance, the same thing, right? We take the difference between sort of the observed and the mean of that. We square it. That's how we're getting the sum of squares. When you see in that table the sum of squares, that is the sum of squared deviations, right? We're taking this deviation here between the observation and the actual mean itself. We're squaring it. We're summing it up. That's the sum of squares, as we're talking about. Okay? So again, that's the sample variance, the overall sample mean. If you want to look at what's the grand mean across all three of my treatments, right? I'm adding up all these observations, I'm summing them all up, and I'm dividing by the total number of observations. So for my experimental example here, if I did, n equals 30 for all of these, right? I would sum all these observations up, and I would divide by the number of observations. I'd be dividing this by 90, and I would get my overall sample mean for all three of these, right? Whatever that is. I'd also have a sample mean for this one. I'd have a sample mean for this one, and a sample mean for that one. This over here is sort of the overall sample mean. It's the average of all of these put together. So again, go back to the table if you want to know, well, how do they calculate that mean square due to treatments? Here you go. How do you do the sum of squares due to treatments? Here's the formula. Mean square due to error. There's the formula. We've got all these formulas if you're really interested. And, I will say this, I guess just to be difficult in the final, I did ask you some questions on this. More appropriately, I actually gave you a ANOVA table with some of this missing. And I asked you to compute it, to tell me the missing values. So, I'm not shining you on this, right? We're going to use this a lot. I think this is important, right? But I don't expect you to sit here and try to understand what every single box in this table means today. But just know that you can easily compute this stuff. Textbook shows you how to do it. I'm showing you how to do it. Okay, so I will ask you some questions from that in our final exam. Okay, and it's going to be, like I might give you this table, for example, and I might say, well, how many degrees of freedom do we have in the treatments? Right? You're going to have to figure that out. I'm going to give you this blank table. It's going to have a lot of things missing. You guys are going to have to plug in some of these to solve this. And you can't solve this cell, right, unless you knew what the sum of squares treatment is and the number of degrees of freedom. That's what the formula is here, right? This formula for this cell is the sum of squares treatment divided by the degrees of freedom. That's what's in this one. What's the F value? Well, again, F value, we have a different distribution now. It's not a Z, it's not a T, it's an F distribution, right? We use this, we're going to use this going forward for ANOVA and for regression analysis. The concept is the same. The area under the curve sums to 1. Okay, so we're trying to understand how likely is it that we get something way out here. This is our p-value again. It's only going to have one tail. It doesn't really have another tail. right? We're only just looking at this p-value. So we get an F statistic. We can convert that to a p-value, right? How do you compute your F statistic into a p-value? Well, there's your F statistic, right? And then your p-value. We're going to literally look this up with Excel, or it'll give it to you. Excel's going to give you this. It's going to tell you what the p-value is. There's only going to be a p-value for the treatments, not for error, not for total. It's just for the treatments. This is based on the degrees of freedom. So again, let me just go back to this. I'm not going to dive into this F distribution. You have tables in your book, but this is all going to be given to you in the output. Just remember, the concept's the same. Area under the curve sums to 1. The p-value is going to live out here in the tail. It's going to tell us how likely it is to get this kind of a result due to chance alone. Okay, that's all p-values for percentages. So, yeah, let's demonstrate how easy this is. Let's just do one and then we'll take a break. I think we're due a break, aren't we? I can never tell. I never take a call. Chemtex engineers are considering 3 assembly methods. So again, if you're reading this problem on your final, you see 3, right? That should be a trigger. I got 3 means. I can't do this. I can't do that, right? It's this right here. We're doing an ANOVA, especially if we're talking about means. That's really the only tool we have here to analyze means. If we have 3 or more proportions, then we're going to use this other test we haven't gotten to yet. But once you see 3 or more means, you got to think ANOVA immediately. Okay, and Chemtech, let's get Chemtech. I'll just bring up here. Don't even bring up mine. I'll just bring up your file. Okay, so here's Chemtech. We want to run an ANOVA, data analysis, ANOVA. Look at our choices. Single factor, 2-factor with replication, 2-factor without. We only have 1 factor. We're only asking 1 question about here. Are these means different? Right? We might get into this a little bit with some examples. I'm actually not comfortable that Excel does a good job with 2-factor ANOVA with replication. I might have a problem. We'll explain that to you. I actually do this a lot. I do 2-factor ANOVAs with replication, and I can't get my results out of Excel what I'm looking for. Okay, it's just not quite powerful enough to actually give us all the statistical tests that we need to report this in an academic paper. So this is where I leave Excel, right? When I have to do more difficult ANOVAs with more factors, it just doesn't quite give us everything we need. But for our purposes here, it's going to be fine. So we've got a single factor ANOVA. The input range, here it is. Is it grouped by rows or columns? Columns. So we check columns. Labels in the first row, alpha 0.05. I'm going to click the output range. Let's put it right here. Press OK. And there is our ANOVA table. Okay? Notice we have some nice summary information up here. Right on each of these columns, so we can see what the mean is, what the variance is, and why do we care about variance? The assumption with ANOVA is that all of these samples have the same variance. Okay, that's close enough to be the same variance. Okay, we're not talking about identical variance here. But if you saw something where the variance was twice as much or 3 times as much as one or the other, we might have an issue here, okay? And we wouldn't be able to accept the results of ANOVA. So we get some summary information here. Clearly, we have differences in the means. The variances are close enough, okay?
And you know that because not just by looking at it, but
yeah, I know by looking at it. I'm just speculating by looking at it. Right. Before that would be a problem. It would have to have a lot more variance in the variance than that.
the p-value doesn't tell you that.
No. I think is this called sphericity, Matt? You ever get involved in that?
No.
Well, when you do repeated measures, you not only have to worry about the variance between the items here, but you actually have to worry about the variance between each pair of items. All right, but we're not worried about that. This isn't another MBA stats class for you. Okay, but you can just eyeball that. We're not going to give you problems you can't solve, right? I'm not going to give you an ANOVA problem and then so you can't use ANOVA because the variances were. I'm not going to do that to you. I want you to run the package and interpret the results. So this is close enough for variance. Clearly, we have some differences in the means, but now we're asked the question. This is our ANOVA table. P-value. Is this result significant?
Yes.
Yeah. So our conclusion is the means are in fact different. Again, you're tempted to say, well, it's probably the difference between 52 and 66. Maybe it's the difference between 52 and 62 and the differences there. We really don't know. But at this point, all we know is that we are getting a statistically significant difference. And that's where we're going to stop. So again, let me just finish this so we can do another one when we come back. So I'll point out a couple more things. Again, actually, I do want to show you my worksheet here for ChemTech, not this one. Okay. So just for that, let me just rerun this ANOVA so I have the results here on the same page.
Good to go. Is it okay?
All right. So now I have my ANOVA results, and what I wanted to show you, this reason I have my worksheet up here, it's the same as yours. I actually calculated these sum of squares just to show you what it means and where it's coming from, right? Because we have them reported as between groups, within groups. So what does any and all of that mean? Well, look what I did over here on the left-hand side. I took all of these data and I put them all in one column here. Okay, just for my convenience. But I sort of kept a little label here, a colored label, so I know which is from which. Okay, so I basically just took method B and method C and I pasted them down here. Okay, so here are my sum of squares total. And look at the number I got. In the report, I got 860. When I calculated manually, I got the exact same thing. And how did I compute that? Just look at the formula here. I took the difference between the observation, that right there, x sub I, and I said subtract the grand mean from it. And where is grand mean? I put a range name up there, right? I actually called this the grand mean. And how did I get that? Well, it was just the average of all of those. Like I was saying over here, right? The average of all of this information, right? Regardless of which sample you're in, I called that the grand mean. And so when we look at the entire variation in the data set, right? Now I know what the mean is in the entire data set. So my formula simply looked at every single one of these observations. I subtracted the grand mean from it and I squared it. This is the sum of squares, right? I found the difference and I summed it up. I'm summing it up here. Here is the difference squared. And then down here, I'm going to sum all this up. And I got 860. Okay? That's just the sum of that column. And what is that? Again, conceptually, this is all of the variation that's in the data. Right? We're not partitioning it out by means. We took all of the data with one swipe and we said, well, how much variation is in it? Well, that's how much variation is. I took all of that. I took the sum of the squares difference, the difference between each observation and the grand mean. I summed it up. I got 860. Now let's look at the next column. In this column, okay, I took the difference and I subtracted that, I took the difference and I subtracted the method mean. So for this group, I used 62 as my point of difference, right? Because all of these observations were from this method, which had a mean of 62. So I use that in my formula for these observations. In the next set of observations, it's the exact same type of formula. Let's just look at that. In the next set, okay, I used 66. Why? Well, that's the mean of this method. Okay? My method mean, if you will. And I took the difference and I squared it. I'm summing these all up here at the bottom. Okay, and the same thing for the final one down here. For any of these that were painted red, I took the difference to be 52. Again, because that's the mean of that method. So what we're trying to do here is we're trying to argue, well, how much, right? How much of this is literally explained? How much of this variance is explained by knowing which method you came from, right? Which of these means you were in? And we discovered that that explains, or that accounts for 340 of the sum of the squares. So the between groups is simply the difference here, right, of 520. Because we know the total variation is 860. When I did this, observation by observation from the grand mean, I got a difference of 860. That's where that 860 comes from. It's all of the variation. And then we're saying that the between groups, the groups, within the groups, is actually explaining 340 of those squared deviations. So the between groups must be explaining the rest. There's no other variation there. So out of all of this variation, knowing which group you're in is explaining 520 of the 860, squared differences. And we know we have 3 groups. So the degrees of freedom is 3 minus 1 is 2. Again, mean square, we have an F, a p-value, and we would claim that the between groups is in fact significant. Knowing which group you are in here explains a significant portion of the variation that you're seeing. Okay? All right, let's take a break.
So it's greater. So we're it's 9.17 versus 3.88. So you're going to reject the null.
Well, let's just look at the p-value, right? Let's look at the p-value. This F statistic, again, it's very similar to Z's and T's, but it's a completely different distribution. It has sort of different range, if you will. Let's just focus on the p-value. This is telling us what's the probability of getting this result due to chance alone. And the answer is it's pretty damn unlikely. It must be due to the fact that there were differences between these treatments, right? These treatments were actually causing these huge differences that we see up here, right? These differences of 62, 66, and 52, that wasn't due to chance. There's something in it. There's something about it. So we're claiming that getting these kinds of differences and getting them explained by the groups they belong to can't be due to chance alone. So we would assume we would reject the null hypothesis that these means are equal, and we would basically get a significant result here. But something about these treatments is in fact causing these means to be different.
Yeah, it's critical that you compare back to the F to see if you're within or outside.
Exactly. This critical F and the F value is the same thing as we were doing before with the Z value and critical Z, right? This is clearly way out on the tape.
Right. Outside of the
It's out, right. It's beyond. Well, this is one of the same. This F value is marking what that P value is. This F critical, this is what, if you were looking at, again, like a 95% confidence interval, alpha of 0.05, right? If that was right at 0.05, this F and this F critical would be the same. This is just a statistic. This is where we're drawing the line, right? We're saying if we get an F value greater than that, we're getting a statistically significant result, just like we did with the Z value. But let's really focus on the P value. But that's what this is telling you, right? If we got an F statistic greater than 3.8, it would be significant. Well, our P value is telling us that.
So what is it, within group study, is it saying anything from that analysis or no?
That's just accounting for the rest of the variance, okay? Yeah, and some packages label this differently. You're gonna actually see, if we were to add more complexity to this ANOVA, imagine we collected not only method, but gender or age or some other information, we did some ANOVAs. We would actually get some more explanations here, but the one we're interested in is really this notion of between groups. Is there a significant difference between these groups? And the answer is yes. Okay, because it explains 520 squared, right? Sum of squared deviation, and the total variation in the three samples is 860. So the within groups is simply the difference between those two. So this is explaining a significant portion of the overall variance, right? We're analyzing variance, we're partitioning variance, and we're trying to understand, well, how much of that variance is explained by knowing which group you come from. And that's an awful lot. Okay, that's a pretty significant result. 0.003, that's highly significant. So again, these tests, easy to run, right? Choosing the right test is going to be part of your challenge. But again, 3 or more means, you have to ANOVA. Just interpreting the results is going to be the real key. And you don't have to do this sum of squares. Okay, I just did it just to demonstrate where these numbers come from. You can really create these numbers. And the fact is, right, we are trying to understand how much variance is due to knowing which group you came from. Right? Here's the total variation. This is how much is explained by knowing which group you're in, right? That's what I did over here. We figured out which group you were in. And so that's why we took the mean of that group, not the overall grand mean, and we were able to explain a big hunk of the variance just by knowing which group you were coming from.
So if they're reversed and the top number was 340 and the within group was 520, what would that tell you that your test data is better, that your group data is better?
Just my impression is, like, if these numbers happen to be reversed, it would probably still be significant. It probably wouldn't be as significant. My sense of that is, we can compute this, but my sense is it would probably still be significant. It just wouldn't be as significant. Okay? Let's take a break and we'll come back to this again. You guys tired? You don't want a break? If you're tired, take a
I'm tired to take a break.
Oh, sorry. Yeah. So, that's how you do it. The point you really didn't have to do it. Yeah. Oh, that was the question is, is this knowing which group is actually fine or part of the variance? No, I couldn't. Well, probably. I wouldn't take it that way. It's probably the reject number. We'll run some tests where so much extra. What the question is, this particular question. And that p-value. So the way I was thinking about it is, what's the problem? This is what each group's average thing is different. What's the problem? That's the claim. That's the alternative. How much? No claim is their thing.
That's what they want.
Yeah, all right. For willing to accept it, 5% chance.
Their claim is the same.
Even less than 5%. Less than 5%. Yeah. Yeah, you guys really don't have to do some square stuff. I just did it to show you one's there, right? And that's the concept.
So you're trying to prove that they're different. So you have a number that proves that they're different.
Well, let me ask you this. You see how these things sum up, right? These sum up. That sums up. The degrees of freedom sums up, right? So I could literally not give you, I mean, just to show you here, I could literally not give you that or that, and I could ask you, what are the degrees of freedom? Well, you know what? We had three means, right? We had three different means. So the degrees of freedom here is going to be n minus 1. Right? This is literally going to be 3 minus 1. And now that you have that, you know, yeah, now you know what the total is. Again, how would you get the mean square? What if I left that number out? How would you possibly compute that?
Everybody's talking about
Well, let's look. If I wanted to, I asked Chelsea.
Chelsea's found out that all she has to do is argue grades.
Sum of squares divided by the degrees of freedom.
No, I'm really glad you did that, and you did it nicely, and I learned from
Be a little
it.
puzzled back and
I was
forth.
like, what's that?
Oh, yeah. And she said nothing. I missed it. It was totally robotic.
Because I was like, I'm way off base if I get
So
that
let's
right. I don't know
compute
what to
that,
get.
that 260,
Yeah, exactly.
that
Yeah.
equals.
And I told, afterwards, I told her, I said, I'm not used to that. I'm not used to like asking you for help or going back and saying, hey, why'd you give me this? I'm gonna start doing it. So I told her, I'm gonna read my
Even
grade
the
and
F
go back, come back and ask you questions.
Okay, you can compute these F values as well. All right, there's formulas for that. I don't know if I'm really prepared to answer that question, but it is equals F dot distribution.
I think I remember you telling me
I'm
what
way
they
past
were.
this.
I know, you done this.
Yeah, I mean, there's a formula. I mean, I'm not sure, I forget what some of these parameters are, but I think it's really,
And that's why I was
the
like.
F distribution is the mean square error divided by these 2 degrees of freedom. Or parameters of those 2 degrees of freedom. Let's just see if that's right.
Yeah.
That,
She graded well, she found some grammar errors. She read them. She wasn't looking at that, she was grading on the back. That's why.
no, that's not quite right. I'll have to, I know you can do this, I wasn't prepared to.
I know includes more on like
Yeah,
Paragraph.
I think that should be right.
I really like paragraphs about our back.
Yeah.
I like.
Oh, there it is. The F statistic, there it is. Duh. It's the mean square divided by the mean square error. So it's this cell divided by that cell. I should have known that. So again, we'll go back to our table.
Right, yeah.
Noise canceling headphones.
There you go. Okay? All that stuff is there. Then the p-value, again, I know this is here too, this equals. I just forget which one of these it is. Turn the ratio, F probability distribution.
That would be to turn off your phone. Yeah. All emails and text messages.
Oh, no, they already did that. I'm still PO'd about that case and the way they treated it. I don't want to be on the wrong side of me if I'm on the HOA board.
Good to see you.
See, couple of weeks.
Yeah, you can straighten them all out and all the bad things I told you. Go over those formulas if you want. You gotta
I
go
thought you
over
were
them.
gonna, well, it's probably one other thing.
So I'll see you guys again Tuesday. We'll have class, 6:30. And then the 31st and the 1st, we'll have classes for those days.
Is there a chance
You guys, you were trying to break down this.
or you didn't see that?
I think the first week's safe.
I just, for me, because I live in, it's hard for me to come. But if it's on a Thursday, that can take class. And it's
Ready for some
11:30.
consensus?
Yeah, I mean, you guys can all vote on that. If everyone wants to the second, I can the second.
But it's also, isn't it due like or the homework's
Midterm
due?
already
Right,
due
their
though,
neighborhood.
before that.
What are you gonna do to fix this?
Look, I could, guys, I could easily postpone not postpone the midterm, I can give you a later due date on the midterm. But also understand, if I do that, you won't have to grade it when we come to class. I can't give you Thursday night at midnight and then grade everything by Friday.
Why not?
Yeah, why not? That's fine, seriously.
I'll see you guys.
Okay.
Take care.
Thanks, Matt.
Good luck yourself, Bob.
I know.
Painting a picture that I couldn't have.
He wasn't thinking of it. Yeah, right?
Yeah, I kind of was.
Right? Like there's some family drama. Yeah, like in Euroculture, there was. She doesn't like it. Oh, there was family drama.
Yeah.
No.
Yeah.
The nephews of the. They said that she's just like a very.
Yeah, Widow Brand, they're like trying to get them.
Really? Okay. Yeah, I thought you would make it like that. Okay.
And then she didn't like the nephews.
Wow. Did she let them buy?
No, it was given.
I thought it said they bought the plot, but she kept them up. That's what I thought it said.
Yeah.
Yeah. Yeah. You know what was interesting? The way you presented everything. The way it came across to me was that you were trying to push off your responsibility, and it was like,
It's kind of like an
you
adult
need to call
onesie, right?
the aunts, and you need to call the cops, and you need to do this, and you need to do that, and I was like,
And that was the
wow.
direction, yeah.
Wow.
We
So-
called them out on it too.
You did you? Okay.
Yeah,
I was like,
That's a lot of us. I practiced it.
it still doesn't, it didn't come across the way it's really good. But I'm skewed because I worked with contractors. I've been on the business contractors and I've been the contractors. And I know that. And I try to do but I am. And I was a contractor, I didn't defense, so. Everybody thinks it's down there to teach.
Yeah, so
And
it's
they're
more stay in
and they're
time.
a fair time. I learned so much from one of my contractors. I mean, I figured out
It was fun.
because I
one
didn't
song
own
I
it.
want to hear.
And my contractor told me that, but in here, I had, oh,
Like, you can play that.
well, I love it. I saw him at a grocery store one day, and he said, man, you're gonna kill you. You're like general conditioning, Jack, and blah, 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 blah. And I'm like, well, year and a half later, that's how I rebuilt the relationship. Yeah. I love that job. That's really fun.
After my life, too.
We may or may not go home and change the direction. I have second row tickets, so.
See, that's interesting. Yeah.
Did you charity homes get changed?
Yeah, totally. Yeah. Yeah.
Times the concerts.
Well, it makes sense now. Yeah. And again, it just sounded like you were pushing off.
She was.
It's like, dang, I know. They would see. Oh, say it again? I don't know. I just sent him a text message and he's supposed to let me know. So I'll let you know. That's what I was doing until 11 o'clock, 1 o'clock. I think 11 o'clock last night. I can't even remember now. Yeah. Oh, yeah. I was dragging him around though. I'm like, we have to clean the garage. We have to vacuum the floors. Blah, blah. Oh, yeah. I was up this morning washing off the tables outside. The beer pong is outside once it gets too windy, then it's going in the rows. Yeah. The keg's outside. What's that? No, what's that?
It's a race.
Okay.
People on each side of the table.
Okay.
But you
Can't do it.
you've got your red color
Solo
house.
Okay.
You got 5 people on each side.
Okay.
Their teams. You start with the first guy, and they take the shot, and you gotta sit down, and you gotta flip the cup, and get it to land upside down
Okay.
Land.
before the next person can go.
Oh my gosh. Okay. I'll watch. I'm not a beer pong person. I don't know why, but I mean, I like watching it.
It's not fun. I suck at it.
You-
It always makes us lose.
Yeah.
And he just ran.
Hopefully it won't be too cold. Yeah, we're hoping people will be able to move in and out from the garage to the backyard, the front yard, you know? Or, not the front yard, the house. From the garage to the front yard. Y'all can't come in the house?
They were like, they did like a fly down and then you have to like land and then take the shot and then do the flip cup.
Oh my
Like
gosh.
8 of them.
Oh, no, I've never seen that. Everybody's eating ice cream. It's tasty. I reject that assertion.
Reject the null
I
hypothesis.
rejected the whole hypothesis to not have ice cream and.
Okay, someone email me midterm.
What?
The midterm, someone email me the midterm. Just
Yeah.
one person.
One person?
Yes.
Email them.
Yeah, let me just show you my book. Let's just assume it's the same.
No, he's asking you to.
Yeah.
Oh.
Sure, Charles.
President Doyle.
So, again, it's the same. Here's the back of the book, in chapter 9.
I don't think we
it
get
tells
it
you
till-
exactly what data files we have.
Oh, okay.
And tells
Yeah,
you.
yesterday. Yeah.
Yeah. So, yeah, if you've already done golf tests, right, some of these coffees.
Is that not starting?
Yeah.
Yeah, it's like
I don't think.
3%.
Yeah, you want mine?
Yeah, you can just find it.
The volume's kind of weird.
Yeah, and then, again, you know what the questions are, it kind of tells you, like, here, this is where I got based on.
Cool, thanks.
I didn't actually, I used the data, but I didn't actually use the questions. It probably is.
Last most recent.
There's no homework.
No, the one right there is
Yeah,
95.
chapter
The
nine.
midterm is-
Yeah,
yeah, that was yesterday. 5 o'clock.
See how close it is.
Yeah.
You guys have his rating, your rating.
Oh, no, that's the exercise. But it actually says it here.
Oh, right, okay, so what's, Bayview, I'm not Bayview,
And then there's a
child
marriages.
care or something.
So they added this
Yeah,
one.
and, clinic care, coffee, Eagle. First,
That email.
Well, we got foul, golf test, so yeah. They just do some minor changes, but yeah, we can open up any of those. Yeah, I mean, because you got the data and you know how to match them up with the problems. In fact, most of these have used data. They actually tell you. Yeah, stock price, this is the question for this data, that data, that data, so yeah. Yeah, I've recommend that.
Is there any,
Yeah, it seems you have trouble with most. Maybe it's just a conceptual thing, or maybe it's a problem. I'll be there.
Hello.
well,
If you, take one of the yes.
And like the weeds too.
that's on my.
I think it might be Swedish fish there.
So there's myself. Yeah, you know, you can't make it, you start traffic. Just, you can text me or call me or something. I usually have, I'm not, you already used that. Okay. I have one. Younger generation. I have an iPhone 5. I think I get maybe a 6 or 7. My wife and I have been talking about getting 2 iPhones for years. We keep saying, oh yeah, let's get a new iPhone.
Where's your phone stop?
Yeah.
Yes, sir.
No, I know, that's so embarrassing. Yeah, all the places they could afford it, they literally, gave her an office right next to mine. It's fine.
Yeah.
I see it.
If that happened with my wife and me, I'd probably just be, you know, a big figure and have a holiday.
No, we get along well. You know, we're not married for 39 years.
Yeah.
Right, get along.
Sure.
I would think so. I think we have I think we have to do this about retirement. Yeah.
Right, doing each other's.
She's actually good about me because I take vacations without her. And she doesn't seem to mind. I don't take many. I don't go to like far off places. But I go skiing an awful lot with her. I usually take a boys trip once a summer. You know, it's not like we go out drinking and morning around. It's literally we come back exhausted from climbing the peaks or skiing. Drinking is not a big part of it. Right to it.
Right.
I tell you, the older you get, I can barely drink more than one glass of red wine a night. I just can't do it. Headaches. Fall asleep. You just can't party. You have to stay in shape for that kind of behavior. You really want to be a hard party. You got to stay in shape. Drink regularly.
Alright, somebody needs to post all the things. How we do it. Somebody go take a picture, needs to post all the pictures.
So Greg, Rebel Oil?
Yep, I left there in June now.
No, that's your old place. Still a controller though, right? We talked about this before. How is Rebel Oil doing? Was it doing pretty good?
Yeah, they sold all their stores. Almost 2 years ago now. So they don't own any of the convenience stores. They still own all the stores. And they have a fuel terminal and 20 trucks. So they still deliver fuel.
What trucks do you leave?
I don't know. I was kind of just bored.
Make more money, more opportunity?
Yeah, I'm hoping.
You're a CPA?
Maybe they saw the video a little too early.
You have to take a realize that it's fake.
I found out this counts.
That's my next question. I was gonna ask you, how much of this counts? I guess it all counts, if you take accounting for it.
I mean, I only need 40 hours a year.
So you'll be doing for 2 years.
I think somebody, yeah, he's like one class. 24 hours.
Can't bankroll.
A lot more expensive than
All right, guys, ready to do one more?
guys.
Do it.
Yeah.
1 more hour, we can do it. We're starting on an hour.
Someone can take mine.
Yeah, somebody have mine too.
I'm ordering stuff.
That's not a big deal.
So before I get rid of this, I was just playing around with this file. You know, we have Excel functions that you can use to calculate some of these things. Some of them are obvious, right? I mean, date 60 is just a sum here, and I showed you how to do it if we're actually going to, compute this number using the raw data. But if you just had the table itself and you were missing certain values, well, here's a couple I computed with formulas. Okay? And again, I'm not going to really get into this. We'll show it to you. We can do this in a review or something. But how did you get to 260? It's a 520 divided by 2. Again, where do you learn how to do that? Well, there it is. right? It tells you right here, right? The formulas are telling you, yeah, how do you get the mean square? Well, it's the sum of squares treatment divided by the degrees of freedom. How do you get this one? Well, this is the sum of squares error divided by the degrees of freedom. Right, so these are very easy to calculate. I think this is going to be helpful for you to do it. Out here it gets a little more complicated. How do you get the F statistic? It's this one divided by that one. Okay, this divided by that is F. There's a formula. And again, if you just, I'll show you in my example here. All right, so how did I get that F statistic? I mean, it is that simple. All right, we're looking at this mean square. This is the mean square. Think of it as, well, it's the sum of squares. We adjusted it for the degrees of freedom we have. So we have a mean square. And I divided that. It's 812 divided by 813. Okay? So that's how I got the F statistic. It's this divided by that. It's a pretty simple calculation, actually. Right? And how did I get the p-value? That one I had to look up. Okay? And again, how did I look it up? Well, there's an f dot distribution dot right tail. And I just filled in the parameters. I gave it the F statistic. Then it asked for two other parameters. What were the degrees of freedom? Let me just bring this up so you can see what it was asking for. It asked for X, right? X being the F value, and it asked for the two cells where there were degrees of freedom. And once you do that, you can get what the p-value is. F critical, I don't know how to get that. I actually know how to get it, but I don't think I'd ask you. You could actually pull it out of your F table if you really had to do it. Okay? But let's not worry about that. I don't think that's one of the ones I'm going to be blank. But the point is, I know that in the final, I've already built the final, that I'm going to give you one of these tables and some of this data is going to be blank. Okay? And you're going to have to fill it out. And I think, again, I've got the formulas. I have pretty much everything right here to do it. You might have to work yourself from left to right, right? You can't just jump in and compute the F statistic because you're going to need this and you're going to need that. And to get that, you're going to need this and this. And to get that, you'll need that and that. So you're going to have to sort of work it from left to right in some sense. But anyway, yeah.
Could you post or email that to us with the method mean and the grand mean?
Which one was that? Is that this one?
Yeah, I think so.
Yeah.
It was.
Have access to that?
Oh yeah, I'll be glad to show it to you. I can email it to you. Email it to everybody. How about I do one? I'll put it on webcam.
Yeah.
Okay, and if you're wondering why, I've got those two ancillary files out there, beer preferences, and that's reminded me today why that's out there is because you guys are probably going to want that one too. Okay, because that's what we're going to turn to in a couple of minutes. But I'll be glad to. And let me just finish.
So is that some of the squares things that we need to have to know how to do?
No,
Or do you
no.
look at that as an example?
I just did it as an example, just to try and, again, try to get you to understand the concept, not necessarily the mechanics. What is ANOVA? It is analysis of variance. It's partitioning of variance. We computed the entire variance, and then we tried to answer how much of that was due to knowing which group you were in. And again, that's what I did manually down here. I literally computed this. This 860 was the sum of squares total. What is it? Well, it's, again, if you look at the formulas in here, every single one of these is, I took that observation and I subtracted the grand mean from it and I squared it. What's the grand mean? It's the mean of means. It's like what I was, showing you an example over here. It's the mean of all of that data across all of the groups together. So I'd be glad to, I'll be glad to name that. I'll put it on webcam, is what I'm going to do. Okay? And I'll make sure that I have the actual ANOVA here too when I do that. But
Isn't that calculation the number that goes in the SN box though? If you say you're going to use it on the test, you can figure it out.
yeah, what I'm going to do is I'm actually going to run a real ANOVA something like this, and then I'm gonna delete some of these cells.
Okay, so you haven't asked us to recalculate that?
No, I'm not gonna, no, I'm not gonna ask you to recalculate. I wouldn't ask you to do these two. I might ask you to do one of them. Right? If I got rid of this one, you could pretty much calculate that, right? I may be able to get rid of, there's a couple things I could get rid of here, and you can figure it out, right? You sort of know the thing has to sum to 860. Same thing here, I can get rid of that. Yeah, there's a lot I can get rid of. Anyway.
You have only formula for the mean square that you just needed, the 260. The formula below. Right there. The zero, the first zero.
I'm not sure which one. Let's get back. Well, I can't. You want what? That?
Age 20. Cells.
Oh.
One more. Above it.
Well, how did I get that?
12 divided by 2.
Again, where is that answer? It's actually, I just deleted something else. It was actually in my PowerPoint slides that I just closed. Yeah. So the answers to all of these things really are right here. This slide is showing you how everything is calculated. Okay? Well, I guess maybe not these, but clearly the degrees of freedom is showing you how you get the mean square, how you get this mean square, how you get the F. P-value, I actually had to do with the formula. But yeah, this slide is really showing you pretty much how where all this stuff comes from. Yeah, if you don't quite understand that, well, that's what all this is about, that I really sort of skated over, right? Nobody's not. It's hard to get excited about understanding all these formulas, but you know, that's what is going into all of these cells. Some people like to see the formulas. You know, I actually like to see them because I think conceptually they help me a little bit when I understand that, oh, that this is, right, this is the sum of squares due to the treatments, because this is the mean of the treatment, and this is the grand mean, right? I know this is a treatment, and I know this is the grand mean because it has 2 bars above it, and it's squared, so I know that's squared, and here's the sum of squares. So it sort of helps you in some respect, you know, understanding what goes into this. But you know, we're not going to actually do formulas. I think that's just a waste of time. So the last thing we have in ANOVA, let's do this. Paint. Open up the paint file and conduct a test. So, y'all got the test result? Okay, so I didn't even read the problem, right? We just conducted a statistical test. We didn't even read what the question was all about. All right, we just went through the mechanics. Right, apparently we have 4 paint samples. I don't know, is that mean drying time? It's mean of something, right? It gave us some summary statistics here. We're going to eyeball the variance. Yeah, it's good enough, right? I'm not going to give you problems that you really can't continue with. Right, this one variance here, paint 3, looks a little odd. There's not a lot of variance in it. But we only have samples of 5 here. It's hardly anything. You're going to see some little bit of variance. So our result, again, we don't have to worry about one-tailed tests here. Our mean hypothesis is that these means are identical. They're the same. So do we accept or reject that at the 0.05 level of significance? We accept, right, the p-value. It's answering the question. This is greater than 0.05. We accept the null hypothesis. Yeah, we can back in. We can see where you get all of these values from. But you know, this is the total. The degrees of freedom is 3. Why 3? We had 4 samples, So n minus 1 would be 3. How do we get that? Well, again, look at the total. If you look at how many observations we had totally, right, we had 4 by 5. We have 20 different numbers up there. N minus 1 is 19. So this number has to be 16. And the rest of them just kind of fall out. And we can run these tests, and without even knowing what the underlying data is all about, we can make these interpretations. So that's how easy ANOVA is, okay? 3 or more means, right? You don't want to do, I've never seen more than 4 or 5 ever done, together. But it can get more complicated with multiple factors, right? Maybe it wasn't just paint, maybe it was the paint and the painter. That would be significant. Maybe it was something else. So you can have more factors than just that, but we're not going to worry about that. That's for your next EMBA class, stats class. So here's the final chapter. I really don't have a lot of slides in this. We're now down to chi-square. Chi-square is for 3 or more population proportions. So again, we're talking about proportions. We're not getting quantitative data. We're just getting counts of things. So you might have to take your data and run it through a count if, so we can get the yes and no, these binary variables. And we're going to show you how, when you have 3 or more of these, to do a chi-square test. I think, again, I'm a big chi-square guy. I like chi-square. It's very simple to do. You can actually do it without a statistics book. It's that simple. So here's some definitions. We've got, our piece of 1, piece of 2. These are our indicators for the population proportions. Clearly, we might have to compute them. But just like ANOVA, the assumption is these proportions are the same. We're testing for the fact that they're different. Again, I'm not going to go through all these formulas, but again, there's the, the expected value. These means, proportions for 1 and 2. Is the expected value of the population proportions are the same. Okay, that's what we're saying. We're using those as point predictors. Again, here's our standard error for this. What is it? This should look somewhat familiar to you guys, right? When we were doing proportions, this is how we calculated the standard error. Well, now it's a little bit more complicated, but view it as sort of this pooled standard error, right? It's a little bit due to this proportion. It's a little bit due to that sample proportion, right? We're adding them together. We're weighting them by the number of observations. But just again, it's the same sort of concept. We need to compute a standard error for the combined number of proportions that we have. You'll never have to calculate that, right? It's just if you're interested, there it is. Okay, and we're asking the same kinds of questions that we did before, and we'll tend to look at this at the 0.05 level if it's not otherwise specified. Yeah, here's the interval estimate if you're interested. I've never used an interval estimate for chi-square or for proportions. I've never used the margin of error, but it's the same thing we've been doing all along if that captures your attention. So let's open this. Tax prep. Read this as you're doing. You're doing it interested in comparing the quality of work at 2 of its regional offices. I'm sorry, this is not going to be a chi-square test. Why isn't it going to be a chi-square test? 2 or more of its regional offices. Right? I forgot what was coming up. So let's just open it up anyway. We're going to get to chi-square when we do 3 or more. So, right, we got 2 or more proportions. If we're talking about proportions, z-test. This is, what is this? This is, well, is that right?
Chapter 11.
Chapter 11.
The tax part.
Yeah.
Chapter 11.
Tax prep, yeah, chapter 11.
So let's just I'll just open up tax prep. Yeah, it's chapter 11, I'm sorry. Tax prep. And tell me you guys got a template too.
Yep.
Yes.
Okay. So again, I'm just going to just leave you with this template. I want to point out a few things on it though. You want to use it clearly if we are testing for 2 population proportions. For 3, we're doing this chi-square. So you have this. It's all built. Again, The sample sizes, notice that they're different. We don't have to have similar sample sizes to run statistical tests. This is a pretty big sample size, 250 and 350 and 300. Just like in the previous ones, I highlighted these yellow. These are the ones you have to change. Everything else is a formula. So if you want to use this template, paste things into it, all right, just remember that, that these are going to have to change depending if you're on using yes or no, or male, female, whatever. So the count of responses. So look, if you look down this column, right, we're interested in how many said yes. Well, we had 250 in the total sample, 35 said yes. And so our proportion of responses, again, is the formula. It's just, it's right, the 35 divided by the 250. So what do we get on the tax prep? We get a Z statistic of 1.645. It's going to be a little hard to explain. Let's give it a shot. The sample proportions, 0.14 and 0.09. The difference of that is 0.05. Okay, it literally took the difference between these. That's the point estimate of the difference. And this test, this interval test, we're going to do the hypothesis test too. But this is basically showing you whether or not, if this contains the interval, 0 is within this interval, right? Between the lower limit and the upper limit, then the test is not significant. The fact that 0 is not contained in that interval, you get a significant result. Okay? Might be a little confusing, but again, this came directly from this comparison. We found a difference of 0.05. Excel went about its way and it put a confidence interval around that, and it shows you well, the lower limit of that. If we want to be 10% certain, okay, only 10%, our level of significance is 10%, then if this interval does not contain 0, then you in fact have a significant result. That's not as helpful as the next sheet, hypothesis test. Okay, same thing. I don't know if your sheet looks like this. We hid some rows down here, right? It goes from 1819, jumps to 250. I just hid some rows in this. And I hid some more rows between 251 and 300. I just wanted you to see that office goes down to row 251, which means 250 observations. Office 2 goes down to row 301, which means 300 observations. Okay? And when you do the hypothesis test, now you're going to get the p-values. So use a hypothesis test, okay? But they're giving you the exact same thing. Now here's our p-value, and our level of significance was 0.1. So if we're doing a, I don't know if we're doing a two-tailed test or a lower-tailed test. Anybody remember? What was this? Two-tailed test, okay? So again, we're going to have to give you this in advance, right? Alpha was 10%, two-tailed test. So we're obviously interested in the two-tailed test. Alpha was 0.1. Is this result significant? Yes, right? This is less than alpha. Our alpha was 0.1. Okay, and we got a result that was less than alpha. So this is significant at alpha of 0.1. Obviously, if alpha was 0.05, not significant. Okay, so interval tests, I'm not a big fan of it. Here's the template if you want to do an interval test. It tells you the same thing basically, right? It's saying that if you don't find 0 within this interval, then it's significant. Okay, at a 0.1 level of significance, that is in fact significant, and our hypothesis test confirms that. At the two-tail, right, it is in fact significant because this is less than 0.1. So that they're showing you the exact same thing. Interval test or hypothesis test. I would prefer the hypothesis test, but again, when would you use this? Population proportions, when you're comparing two population proportions.
For the interval test, you know, like it. But if we change the confidence level, the coefficient is 0.95. We get that negative value now. Is that what you would say would be 0?
Yeah.
So the range contains.
The range now contains 0, so it's not significant, right?
Okay, show you how people.
So again, if you're thinking about, you know, our bell curve, you know, our normal distribution, we're finding 0. We said our hypothesis was there's no difference. 0 is no different. 0 is within this interval, so it's not
What
significant.
happened?
I don't know.
Okay?
Mm.
So,
0 is not.
right. 0 is within, right? Because that's what our hypothesis was. These are identical. That there's no difference. So it's actually testing that. Yeah, I'm not a big fan of that. I like the hypothesis test, but they're one and the same thing. They're just showing you.
Oh, that's great.
A lot of this
Love it.
depends on what information.
What's that on top of your head?
That's me.
Yeah, that's you. You still have that on top of your head. Is that your dad?
This you can do with a
Yeah.
worksheet. I think.
No.
Yeah, I'm not trying to skate over this stuff, but the
Your dad
interpretation
looks like a
just
movie
goes back to the same thing. You're comparing your p-value to your alpha value, or you're comparing your test statistic to some critical test statistic. It's the same regardless of which kind of test you're doing. We're always doing the same kind of things. Okay, so here's building the worksheet. We've already done this, right? I'm not going to do it again. I'm glad I did this in advance and gave me the files, so we don't have to build them. Okay, again, you want to go through all the equations. Here it is. But again, pooled estimate of standard error. Right? That's all we're really doing. We're sort of looking at the variance, you know, the differences that are within each of these, and we're trying to get an average and say that is our average or pooled estimate of the standard error. In our test statistics, same thing. We got a z-value here. We subtract the difference. We divide it by the standard error. We're saying how many standard errors is that difference away from 0? And apparently for here it was not significant. So we did tax prep. Here we go. Okay.
So the tax prep one, the fact that the difference, point estimate difference is 0.05, has nothing to do with the confidence level.
Oh, right. That was just a coincidence that difference happened to be 0.05. If you look at the numbers, it was 0.14 and 0.09. So when you subtracted it, you got a 0.05. So now we're doing that last one, chi-square. Okay? This case, we're looking at more than 2 proportions. They call it multinomial population. We're really dealing with proportions here. We're not getting means. There's nothing you can really sum up. We're going to have to count something and get a proportion. Okay? Once you see it, I swear it's a lot easier to actually do than actually talk about. Okay? Here's the assumptions, right? One and only one of these outcomes can occur. Assumed independence, and they remain the same for each trial. This is the standard assumptions that we make with these kinds of chi-square tests. Again, how do you do it? Well, again, you want to state your null hypothesis. It's typically that these are the same, that there's no difference between these categories, these K categories that we're looking at. Here's how you compute the test statistic. I'll show you this in a minute. This is chi-square. This is why it's called chi-square. What is it? Well, look at it. It's the sum of the sum. It's the sum of all of these deviations squared divided by an error term, just like we've been doing before. And what is this F and E? This is the observed frequency. E is the expected frequency. And then K, like I said, it shows you to be the number of categories. And just like before, we're going to get some sort of a p-value here. And if it's less than alpha, we reject the null hypothesis. Or if the chi-square value is greater than the chi-square times alpha, we're going to reject it. So let me just show you how sort of simple this is. There's auto loyalty. So let's open this file. the auto loyalty file. I'm going to open mine rather than yours. So there's our data. Okay? So what we're trying to figure out, right? We've got a whole bunch of observations here. We have automobiles and whether or not these people would be likely to repurchase the automobile. Let's just go down here to the bottom, see how many we got. We have 500 observations. And we've got Honda Accords, we've got Ford Fusions, Chevy Impalas, we've got all these different car types. And we're asking the question, is there a difference between people who own these cars and how likely they are to repurchase the cars based on these ownerships, right? So it's a very simple data set, right? But there's no numbers, right? The only numbers are the owner numbers, which doesn't count. We have these qualitative data here. So what are we going to do? We're going to do a pivot table. So your pivot table, I put it up there on the top. See if everybody can do this pivot table. I did the response variable across the type of car. So we had 3 cars, Chevy, Ford, Honda, and there's a grand total out here, and we had these yes, no. So can everybody build that pivot table to get that result? I'll click on it if you're uncertain. Okay, here's my pivot table. How did I build it? I took automobile in the column. I took this field likely repurchase as the row label, right? Yes, no. And then over here in the values, I said, give me the count of something. I think I said count of likely purchase. You could have counted automobiles. It didn't matter what you counted, right? So it gave me that pivot table up there. And then just to check, just make sure, right? We had started with 500 observations. We got 500 observations. So you have that pivot table? Okay, now that's the data that we're analyzing. We're trying to understand, well, look at these no and yeses here, right? Are we getting some differences here that are significant? Well, how do we tell? Well, the first thing that I'm going to get you to do, advise you to do, copy that table and put it down here as values. So you get rid of all this stuff, right? I may have already done that. I may have already turned this into values, but no, I didn't. Okay. So all I did was, okay, I copied this pivot table, and I literally just, when I pasted it, I turned it into values, so it didn't come around as a pivot table. Okay? Anybody having trouble with that? Well, let me know if you don't want to just right here. So if I'm going to paint out my pivot table. I'm just pretty sure that's how I did it. You copy, and then when I pasted it over here as values, and boom, that's what I got. Wasn't quite clean, but there it is, right? Same thing that I have over here, a little bit cleaned up.
Why did you paste it as values? And what's he doing? Making
Yeah.
Okay.
You guys with me?
Yep.
Now
Okay. So, if you remember the formulas, let's go back to see what we're trying to do here with chi-square. It says we need to take the difference between the observed and the expected frequencies. Observed and expected frequency. Well, we just calculated the observed frequencies, right? This is what we observed. So I labeled them up here as observed. How did I get these expected frequencies? Well, if you remember back to some of your probability classes, we have these marginal values out here. They're not marginal probabilities, but they're marginal totals, right? This is all the people that said no, all the people that said yes. Here's all the people that had a Chevy, a Ford, and an Accord. With that, we can compute these expected, right? If we ignored all of this table data in the table here and we just used these marginal values on the outside, what would we expect? Well, Again, this is what I said we would expect. Okay? For this cell, it's the my column total times the my row total divided by the grand total. Okay? Let me show you a simpler explanation of this. I just switched to another file. Now let me just keep this in the world of like, 100% here, 100, right? If I told you that there are 60 males and 40 females, and what is this, eye color or blue color, whether they prefer blue or green, right? We don't know what the expected is, we just know what the marginal is out here. Well, again, the expected, I would say that, well, for blue, I would expect this to be the 70 times the 60 divided by the 100. Now, anything wrong with this formula, I'll correct it in just a minute. Yeah, that is right. Okay, 42. And if I did that for all the cells, this is what I would get. So all we're really saying, we're sort of using the probabilities, right? We're saying that if there's no difference between males or females or blue and green other than the totals, this is what we would expect to get based on these marginal totals. Okay? It might be easier to do. You can almost see this with probabilities. If I turn these things into like probabilities, this was 0.7, 0.3, 1, 0.4, 0.6. Now, if I wanted to multiply these out, I don't have to worry about this total. I can just say that I can even get rid of that total. I can just multiply the probabilities together, and that's what I would in fact get, right? I don't want to confuse you here. I'm just saying, if you think of these as probabilities, right? If this is a 0.6 chance of being male and a 0.7 chance of having blue, what's the probability of being male and blue? It's the 0.4, it's 0.6 times 0.7. Same thing here, right? Male and green, here's the probability of green, here's the probability of male. Multiply those together, you get male and green. So that's what we're really doing with all of these, except that because we didn't have numbers, we didn't have probabilities that summed to 1, we had actual numbers, we had to multiply these and then divide by the grand total. I'm not trying to confuse you, I'm just trying to show you where expected comes from, okay? Expected, again, if you don't know, what these numbers are, what would you expect? Well, I would expect that this one to be 0.3 times 0.6, right? The 0.3 chance of getting green and a 0.6 chance of male. And so male and green is 0.18. Oh, I'm sorry. I put it wrong. You're right. Okay? So that's, let me get back to the real world here. That's where expected comes from. So how did I get those expected? Same thing. If you look at this, and I use my range names just to make it easier, right? I basically took the column total, right? Let's do it this way. I took the column total times the row total, and I divided it by the grand total for every single cell. Took the column total times the row total divided by the grand total. That's how I got my expected. So now we have expected and observed. Okay? Now we're going to get the square difference between expected and observed. Why are we doing that? Well, that's what the formula wants us to do, right? The square difference between observed and expected and observed. We take the difference, we square it, and we sum it up. So what did I do in my worksheet? I took that. Every one of these cells is the square difference between expected and observed. So let's look at this 172. What is that? I took that, the observed, minus the expected, and I squared it. I divided by the total. Where's the total? 360.
Yeah.
But they expected no.
I'm sorry, there it is. The formula is say divided by the expected. Okay? So that's why we did it that way, right? And all of these are done the same. We computed the square difference, right? If I look at this one, let's look at the 0.31 here, right? Here's the observed minus the expected, divided squared, and then divided by the expected. So all I'm really doing is I'm just following this formula here. Trust me, it's going to get really easy after this. And we don't even have to do this, okay? We really don't have to do this, but I just wanted to show you how it actually works. So I did the formula. I have my sum of square differences. The sum of all the square differences I put right in that cell right here, right? I summed all of these things up. I put it in that cell. And that is my chi-square value. That is the sum of the square differences. What does that mean? We have to look it up, right? We're looking it up in some chi-square table. Again, it's in your book. But let me just actually show you where that came from. What's the p-value of this test? Well, there it is. Here's the formula for the chi-square test for the p-value. Okay? Returns a left-tailed probability of a chi-square distribution. X is a value you want to evaluate. So I got my chi-square measure, right? The sum of all the squared deviations from observed to expected divided by expected. I got to be 0.89. So all I had to do then was tell it how many degrees of freedom I had. And degrees of freedom that are in the chi-square, it is simply the number of rows minus 1 times the number of columns minus 1. Not counting the grand total. So how many columns do we have? We have 3 columns. So this becomes a 2. How many rows do we have? 2. So this becomes a 1. 1 times 2 equals 2. We have degrees of freedom of 2. Again, this is in the notes. Okay? So it gives me my results. Is this statistically significant? At the 0.05 level? Yes. Yeah, same thing. We're looking at our p-value, we're throwing it up against alpha, and the chance of getting, what's the probability of getting this due to chance alone? Well, it's less than 2%. So we're claiming that there's something about whether you own a Chevy, a Ford, or an Accord, you are more or less likely to say you're going to repurchase that. Yeah, it's not exactly telling us which ones of these is causing the result. It's just telling us that, look, this is what we would expect to get, right, given these marginal totals here, but that's not what we got. That's what we got. And if you could look at just some of these, right, look at Honda Accord for a minute, right? You might expect it to have 66 no's. We only had 52. You might expect for Chevy Impala, you would get 47 no's. And what do we actually get? 56 no's. Okay? So again, this is suggesting that something about owning one of these cars is sufficient to alter this distribution of yeses and nos across those cells. So again, let me show you the real simple way of doing this. Okay.
Oh, fine.
So here's how we do it. Right. We still have to do this pivot table and whatnot. Okay. But you can also, rather than compute these sum of squares, you can just go directly into the chi-square test here. Okay. Notice that I have the exact same results here. I have a p-value. I have a chi-square test, and I simply did it with formulas. Let me show you how I got my chi-square. I'm sorry, I put it on the wrong box.
this is.
Yeah, actually, yeah, I'm just, something I missed, forgot to do something. P-value? Oh, there it is, thank you. That's what I was looking for. How'd you know it was there? Okay. So what do we really need to do this test? All we really needed was the observed and the expected, okay? We didn't even have to worry about this chi-squared, sum of squared differences, right? This is the observed, we got this right from the pivot table. The expected, we had to compute the expected, so we did have to do that, okay? But again, it's just the marginals, multiply the marginals and divide it by the total. All right, every one of these. What's the expected? It's the marginals, 232 divided by the total, and you will get these expected. So just by painting it up, God, we love to paint shit up, don't we? All we really did there for that chi-square test, I painted up where expected was, I painted up where observed is, observed and expected. We open this dialog box up, right? It's asking for the actual range, it's asking for the expected range, and that was all it needed. It did the rest of the stuff itself. It did not, we didn't have to compute, in other words, we did not have to compute this sum of squared difference expected and all that. All right, I just wanted you to show that this is in the old ways. You didn't actually have a stats book. This is how you go about doing it. Right? If you didn't have Excel, you could literally do the observed and the expected, find the squared difference. Right? You sum it up, and you get your chi-square value. You could look that thing up in a table, and you wouldn't even need Excel to do this. You could look it up in your chi-square table, and you get your p-value. So again,
Can you, why is your p-value, yellow p-value?
So
So it's 2, 3.
Yeah.
so I'll bring it up again. Actual range minus the actual range and the expected range, and boom, that's going to give you your chi-square statistic. We don't know if that chi-square statistic, it actually gave us our p-value, okay? It literally did everything in the analysis for us. It actually did not give us the chi-square statistic. All it gave us was the p-value. I should say all, that's really helpful. But again, if you had to report this, to say an academic journal or something, they're going to want to see what the chi-square statistic is. So how do you get the chi-square statistic? Well, again, without going through all this again, here's the formula for that. You can literally ask Excel to give you the chi-square statistic. It asks for the probability, which was that. Right, here's my p-value, and it asks for the degrees of freedom, which is 2. I entered that in, and I got my chi-square statistic.
Would you be able to upload that one onto the web campus?
Yeah.
Why is it right instead of regular?
Why is it what?
Right. Inverse that right instead of just chi-square. That formula. Why is it?
Oh, actually, I think it is only a right tail test. If we actually, there's no such thing as a left tail test, I think. Equals chi-square, okay? That's what we have. We've got the distribution, we've got right tail, there's no left tail. It's just these choices here, these inverses, or where is it saying? Maybe I got my chi-square value back. I forget how they do the books, the tables. Again, we don't really use these, right? You don't really have to look these things up. F distribution. F distribution. Chi-square distribution. They're showing us the right tail in our textbook here. Right. That one you got me on. I'm not certain why those different. We can compute all those and figure it out, which is the right one. But in terms of left tail,
We just are on using, because your P value that you highlighted in yellow there, you just did 1 minus, so I know it's the same thing.
yeah, that's
But if we just did the right tail, you wouldn't need that kind of just the answer.
so. Let's just try that. You just want to do what? Equal C.
You did the right tail.
I did a right tail. So we're gonna just do the left tail. I'm not sure. Oh, let's give this a shot. The X would be that. The degrees of freedom would be 2. And this would be true. I'm not betting on this, but
So that's 1
yeah,
minus.
that's 1 minus. Yeah.
We did
So are we like projecting something?
No, that's the same thing. No, the same thing. The p-value, right? The p-value is telling us whether or not we're accepting or rejecting. And this is what I really wanted to, to show you guys. You don't really have to do this square difference. We can get rid of all of this, right? We can just simply get our p-value by going through the chi-square dot test, observed, expected, boom. It's going to figure out the degrees of freedom, right? You painted up the range. It knows you're dealing with a 2x3 column, so it's a lot easier just to do it with that particular test, doing the chi-square dot test and then painting up the values.
So just to fully understand, so you do the pivot table first, then you copy the pivot table into the values, then you do the expected, and then you can do the formula.
Right. So, right, the actual steps, let's look at what we did. We did a pivot table, so we got the frequencies. And I think this is a lot easier not to mess with, the pivot table and moving things around. So I just copied it. That's how I got the observed. We had the expected, which is, right, you multiply the marginals times each other, divided by the total, and you get the expected. And now you can stop. Now you have enough. Once you have the observed from your pivot table, you do the expected by using these marginals. Okay, now you can forget about the square difference stuff. You can just jump right into the chi-square, the p-value down here by doing the chi-square dot test. Right, you paint up these two ranges, and it knows how many degrees of freedom you have. Right, it does it calculates the square differences and everything for you, and it gives you p-value. The only thing I was going to show you here is, I'll put this one up. You may need to have the chi-square statistic as well. Okay, one way to do it, obviously, is to actually do it old school and calculate it. Right, I mean that's how we did this. We literally calculated all these square differences. We summed them up, and that's we got our chi-square statistic. But to get it directly from the formula, without having to do that square difference, right? Here was the p-value, but to get it down here, I did this inverse, okay, of the right tail test. And trust me, I guessed a couple times. I wasn't sure which one it was either, but I knew it was one of those. You can sort of see it when you get it right. I had something to compare it to too. Right? I knew the p-value was 0.0193 from checking this. Okay. So chi-square clears mud. Let's do one. Let's do one, and then we'll call it. I'm gonna post this for you. I think I have one more up here. Auto loyalty is what we just did. Again, I didn't go through all the slides. I'm going to show you in Excel. Here we go. Here's the pivot table. Copied it to make the observed. These are our expected, our chi-square values, and actually doing all the p-values with Excel. So test of independence, that's really what this chi-square test is all about. There's that beer crate. We're really trying to understand, right, was there differences between car ownership and your likelihood to repurchase? We didn't have any mean data, right? We didn't have any actual data we could sum up, we had to count everything. We did it in that very simple table, and we're actually asking this notion of independence. What we're actually asking is, you know, is yes, no independent of cars? Or conversely, is owning a car independent of yes or no? And we're discovering it's not independent, right? We can't just assume if this was independent, we could just simply multiply these marginals together, and that's what we would get for our observed. And that's not what we're getting.
So that's what it tells you whether or not the two things are independent.
Yeah.
Or not.
Yeah, and it's not independent. If you get a p-value, right, less than your alpha, then these are not independent. So responding no or yes to the survey is not independent of cars. It's one way to say it. Or car ownership is not independent of the yes/no answers. It's one and the same, right? That there's something going on here, right? It's obviously the cars. There's something about this, whether or not you own a Chevy, a Ford, or an Accord. Apparently, it looks like you are much more likely to say yes if you own an Accord than if you own a Chevy Impala. Probably just made up data anyway. Would you be likely to repurchase?
Oh, like there.
Right, that was what the whole problem was all about. How likely are you?
All right, I go back. Thank you.
So that's the whole test of independence, and that's what the beer preferences is. And I don't know if you guys, I put this file out on Web Campus. I don't know if we have it in our set, do we? Beer preferences.
Yep.
Yeah, we do. So we can do the same thing with beer preferences. All right, let's just sort of roughly start here. We're not going to finish it, but just to start, what do I want to do first?
Pivot table.
Pivot table. So I'm going to insert a pivot table. Here's my pivot table, and I'm going to do, it doesn't really matter how we do it. Let's put gender down here. Let's put beer preference over here, and then we have to count something. Let's just go down here, and we're not summing it, we're counting it. Okay, shows we have 200 observations. Is that about right? We have 200 observations. So back to the table. Okay, so that would be our observed. So I'm just going to copy this, paste it right down here as values. Got my values. Clean it up a little bit.
What do you want in values? Is it reference? Or
Yeah, you could have done, it doesn't matter which way you do the rows and the columns, it really doesn't matter. I was more or less interested in this table. Okay, just, I'm not trying to be real anal here. What I really wanted was, I wanted just to make sure that, you know, we understand how many variables we have. So how many degrees of freedom do we have here?
2.
2 again, right? 3, we have 3 minus 1 times 2 minus 1, which is 2. So this is our observed. And again, let me just take this. Now let's call this expected. This is my expected. Get rid of this stuff. I forgot to put the, oops, I have this total here. This. Okay, so I'm going to take my observed, just to use the same column headings again. I'm going to paste it right here. And now I'm going to have to compute these expected. Right? Well, what is it? This cell is equal to this times that divided by the grand total. And I can't just simply copy that, right? So I have to use some relative or absolute cell addresses. So I say when I copy that, what I always want to use the B And that's why I use range. Probably get these wrong. See, I'll get one of them right. What did I do? I missed the first one. Oh, yeah, that's right. Here it is.
That should work.
All right, we're copying it. That's right. All right, check this one. All right, so now we have our expected. Now what do we do? Chi-square test. Chi, yeah, looks like chi. So we're gonna do our okay, so now we're doing the chi-square test. The actual range is this. The observed range is that. And we have a p-value, right? This is our p-value. So is that statistically significant? Do we get a difference in beer preferences by gender?
Yes.
Huh?
Yes.
Yeah, so 0.05, we would say this result is significant. And then if you wanted the chi-square statistic, we could literally ask Excel to give us the chi-square statistic.
Again, if it's significant, it means the variables are not independent.
Right.
Right.
If we get a significant result, we're saying that you know, these beer drinkers, gender is not independent of beer, or beer is not independent of gender. It's one and the same thing, right? We could have taken this, turned the table the other way. It doesn't really matter. And so if you look at the results, right? I mean, this was the observed and expected. Well, it looks like women don't like dark beer as much as men do. It looks like, what else seems to be really out of whack here? Here's 51. Males, they're more likely to not like light beer. Obviously, they like dark beer more than they like, more than females do. They're less likely to like light beer. And I don't know if you see much irregular going on here too. They're less likely to like regular. Yeah, chi-square, I mean, it's the kind of data you see in the real world. I mean, it just fits chi-square tests, right? If you're going to do surveys and samples and get people's opinions and categories, if you can put it in a nice little pivot table like this, well, now you know how to analyze it, right? We're going to do observed, and we're going to compute an expected, and boom, we're going to do a chi-square test, and we're going to discover that, yeah, that these are not independent, so we do have a statistically significant result because of this. Saturday night, what's happening? So I'm going to stop. I think that's the end of it. What else? I'm going to post these files, some of these files for you, and just a reminder. Beer preferences is already out there, but I don't know. Did I give you anything with it or just data? All right, I'll put some of these examples out on Web Campus, so we have sort of the same information, the same formulas of the cells and all that. You can check them out.
Because the p-value is less than 0.05, then there's not whether you're male or female, it's not dependent on whether the kind of beer.
Right. We got a statistically significant result. So our claim is that beer drinkers are not independent of gender. Right? Gender is predictive. Gender is predictive of what kind of a beer you're going to like. It's not the right way to say it is not independent. Okay. Well, right. It is the right. Dependent. right? It's not independent, it's dependent. So you're saying that your depends on your gender. Or you could say your gender depends on the type of beer you like. Right? It's not-
Correlation doesn't.
Right, you gotta be careful when you say it, it's gotta get the right cause and effect. Clearly, it's the, the gender that's causing, is causing.
Yeah,
the
of course.
type
Do whatever
like
you want.
beer or dark beer.
Drinks dark beer generates more males.
There
There you
generates
go.
more attraction to males.
Yeah, and now it's.
But this is a good test. I mean, even I do complicated statistical analysis, and at times we just get qualitative data. We get counts and yeses and nos. There's nothing to sum up. There's no means. You can't compute means or standard deviations or standard errors. All you can do is deal with proportions. It's a great little test, right? We got observed, expected, painted up, bingo, and then you run a statistical test, and you're golden. All right, I'll put these up, not tonight,
Take your actual mass.
maybe tomorrow.
And nobody's looking at them for anyway.
Square, divide